right.
Yeah. And then we can say, can we call the day scientific machine learning as a topic?
Well, I would say that the theme of the day is where humans will go, where human mathematicians and engineers will be in the age of AI.
Okay.
Part 1 is scientific machine learning. Part 2 is agentic AI.
Yeah. So just read it. So you don't need to plug your computer, okay?
Oh, and I'll need a.
Just read from here when you.
I'll need power. I'm gonna definitely run out of power.
Just.
I don't need to introduce him.
You need, but you say welcome to day 3.
This thing will fill my battery. Half an hour.
Explains today is just up until 12. So people are online now, right? And then today is all about, or this morning is all about where human mathematicians and engineers go in the age of AI. Okay. And then now it's with Chris Paukas, and you introduce him. Yeah. Thank you.
I got so much water in my. I look like a madman. There's no
power there.
Okay. With the agents running, I probably am only gonna have like 30 minutes of battery.
Okay. Do we have an extra power strip?
Yeah. Sorry, you kind of need a nuclear power plant for these things.
It's not nuclear, but it will do the.
It's fine. Perfect.
Do you want to do full screen to see? How it,
Yeah, I just checked it. I mean, yeah, I'll be.
presentation, and then- yeah.
Wait, let me double check though what it says. 56. Oh, that's fine. That's fine. I'm gonna cut to live anyways. And that's part 2. So. It's all good.
Good morning, everyone. Welcome to the day 3, where human mathematicians and engineers go in the age of AI. Chris Rokakas, a research affiliate and co-PI of Julia Lab at the Massachusetts Institute of Technology, director of modeling and simulation at Julia Computing, and creator, lead developer of Julia Sim, director of scientific research at Puma's AI, and creator, lead developer of Puma's, lead developer of SciML, open source software organization. I welcome Chris Rokakas.
Yeah, thank you very much. Thank you. Thank you for the kind introduction. I think everyone's going to be streaming in here, coming in from breakfast, and as everyone's coming in, everyone will have this thing on their mind where everyone's working today, but also at the same time you're thinking, am I working tomorrow? Because AI is kind of coming for me, right? Okay, it's kind of a joke, but actually it is the the question that everyone's asking at the breakfast table, right? So I thought what would be pertinent is to update what I've been talking about before. The last few times at JuliaEO, I was talking, oh, here's scientific machine learning. Here's how you do things with AI and machine learning, right? And here's how you make it a little bit better, right? But this talk is really now kind of the evolution of that, to basically just say, here's everything that's going on. Here's how you use it. But here's how you become a more effective scientist. So that way, as these things are obsoleting the old way of doing things, this is how you stay relevant, right? And I want to kind of bring this from the point of not just, how do you write a few things in a computer, what do the scripts look like, what's the Julia code look like, but I want to show you the problems going on, how things are evolving, and what that means for how you should be changing how you do computing, right? So let's start. So let's start with talking about the bitter lesson of AI, right? Because the bitter lesson of AI is kind of the core of where everyone talks about, where machine learning is going. This is something that's attributed to Rich Sutton from 2019, and he talks about this idea that general methods which leverage scalable compute will outcompete everything, right? The idea is actually pretty simple, right? So let's say you have a method that is 10 times less efficient, 10 times less efficient than your very, very detailed thing. So you have one solver that is able to solve all equations, and it's 10 times worse than the type of method that is specific to your one equation. But if you just build a big enough computer, you're good enough. So as long as you make that, as long as that method that is 10 times worse, as long as it's parallel, and as long as you can get a nuclear power plant, as long as you can be NVIDIA and get $1 trillion of GPUs, then you can outcompete the person who is then trying to make a very specific method for a very specific problem, right? Again, I'm not going to say that I'm 100% in this idea, but this is the idea that was put forward, and this is the idea that's driving the AI revolution, right? It's not like, there are some people that are going to tell you that what's driving it is the idea of AGI and, Terminator is going to come for us. No. Like the true idea and computer science behind it is this idea of the bitter lesson of AI, which is that if you work on scalable general methods and then you work on making it so that way they just scale for lots of compute, this is a tool and a method that can outcompete in many scenarios, right? And so where Richard Sutton really talked about this is the idea of, if you look at what happened with chess, right? It took decades and it took a lot of researchers who knew a lot about chess to be able to beat Deep Blue. And it was just barely able to beat a grandmaster, right? But what happened next was general methods. So a method that was just say, okay, it's not really a bot that is for learning how to play chess anymore. Let's build a reinforcement learning agent that learns how to play games. And let's let it play 1 trillion of these games on tons and tons of compute. And this is what you get with the version that started being the alpha, all the things that you start with going with AlphaGo, and suddenly you start being able to say, oh, chess is an easy game. What about Go? What about StarCraft? And basically you start to have a method that scales to all these different methods. Now, it takes $1 billion of compute for this technique to work here, but it was something that suddenly was able to unlock the code to say humans are no longer the thing that that will win at almost any game. And it was not by creating a bot that is better at Go, not by creating a bot that is better at StarCraft. It's creating one method, a reinforcement learning method that is built on scalable compute and just scaling that compute to astronomical levels, right? And so this is also where speech recognition and all this stuff with natural language processing came along. Right? Instead of saying, hey, look, let's build a database so that way we understand the word in English, we understand the word in Spanish, and now we have translations between them. Oh, now we have to repeat that work when we go to Portuguese, right? That's not how all these machines started to work, right? You had one thing where you said, okay, let's build an engine that is able to take a corpus and text from one, and is able to take a corpus and text from another, and is able to learn the translation between these using translated pages like Wikipedia and these sources, right? And now let's just take this and just make sure that we put into it trillions, of gigabytes of data and trillions of compute, billions of dollars in compute. And if we do this scalable compute way, sooner or later, it will outcompete the experts building a translation engine, right? So this is the bitter lesson of AI, that what has been learned through decades of AI research is that these general scalable methods outcompete experts trying to build expert machines. And this seems to be quite the path where a lot of things are going, right? And so, again, I'm not saying that this is where everything is going, but this is really the core thesis behind the AI revolution, that sticking to methods that are scalable and general ends up outcompeting the things that are specific to domains. And so one thing that we need to then kind of understand then is, okay, that should be scary to hear as most people who are scientists, because what you do is you build specific methods for specific problems, and so you must go, oh, am I going to is there going to be a general neural network that will start to build a climate model better than me, right? And so I think that that's not really the right way to think about the problem for where humans will be in the near future. I think what you need to start to think about is, where do these methods have issues, and how can humans be the ones to cover those gaps, right? And so let's start to investigate a little bit of this. So one potential problem that happens in all these different systems is out of sample data, right? So basically when you train all these systems, right, they don't actually know anything, for example, about language. When you're training a system that is doing translation, it just knows all the language that's there on the internet, right? And it's going to learn sooner or later everything that's written on the internet, how to translate from language 1 to language 2. But what's something that's out of sample is, for example, all the stuff that comes up with slang, right? So, if, for example, in Terceira, there's all this random slang about, for example, getting hit by the fifth bull, right? So there's 4 bulls that come out in every bullfight, and the 5th bull is, when you get hit by the hangover, right? So, this is something where if you try to put this into Google Translate, it will never learn this because there's none of that corpus in there, right? And so there's still a place for humans to go, which is understanding where the data doesn't work, right? And so I think that this is a great example because here's an example of a Tesla. Where there's a full moon out there, but the Tesla was never trained to be with such a large full moon, and so therefore it believes that the moon is actually another car, and it slowed that in the car and almost caused a car accident because it saw this gigantic moon, right? So this is where you can start to see that, yes, a complete learning system, if you give it infinite amount of data, it will be able to do everything. But in the real world where you don't have infinite amount of data, there are certain things to be able to program into the system, like the moon is not part of the moon is not part of the Earth, right? That even though that is a light, we know through certain information, things like parallax, that light signal is actually so far away that you shouldn't be considering it as actually in front of you, right? And this is some kind of information that we somehow need to be building into our systems. Another really great one is, so here you can see there's all these traffic lights that are hitting the car, right? And we'll see in a second that it's actually just driving behind a truck that has traffic lights in it, right? And so again, this is not a scenario that was part of the training of the self-driving car. And so the self-driving car engine just has no idea what to do when it's driving behind a truck with traffic lights, right? And so these learning systems, they technically work in the ideal world if you have infinite information and if you've seen every single possibility. But this shows you that there's always possibilities that you don't run into. And what humans can start to do is start to cover these gaps for which, because we can extrapolate out and understand that is a truck with traffic lights in there, but a system that does not truly understand what's going on in the world will not be able to make that extrapolation, right? And so this is one piece that we can start to think about, right? That what humans have been able to do, that AI and machine learning is not good at all. Even after $5 trillion of putting work into this, even after all of this, ML and AI does not generalize beyond the data sets that it's been working on, right? So how is Sam Altman trying to deal with this? How is Google, Satya Nadella trying to deal with this? They're just trying to find more and more data to be able to cover literally everything that's going on. But if you don't believe that you can literally get data for literally everything, then this tells you one thing that a human can do, which is to help make sure that what the behaviors are of these systems when they're going beyond their data set, when they're trying to extrapolate beyond, right? Trying to make sure that we can control, constrain, and understand what's going on beyond the training data set. Now, here's another thing to take a look at, right? AI and machine learning really started to take off in areas such as playing computer games and video games. Now, why is this the area where they started to do a lot of their work early on and show a lot of their demonstrations? The reason is because it is exactly this kind of scenario where you can get infinite data and the data is perfect, right? So all these groups like DeepMind and DeepMind was a really big one, right? They got billions and billions of dollars, and they said, how are you going to show me that AI and machine learning is going to work? Well, they said, we're going to make it play Mario first. We're going to make it play Go first. Why do they do that? Well, because inside of the game of Mario, you know exactly all the parameters. You don't have this real world thing of like a truck with traffic light that comes in. There's one game, and you can play the game infinitely number of times, and so you can get as big of a data set as you want. And so basically the AI and machine learning companies, right, really started to say, we were going to show everyone that the whole world is going to change once we get enough data by using this as our playground, right? OpenAI and DeepMind did this. And they did it, right? They showed that with infinite data, they were able to beat every human at Go, beat every human at StarCraft, beat every human at pretty much every game they threw it on, and they said, this shows us what the future is going to be. But I think actually it was a double-edged sword, because it showed us that it could be the future, but it showed us an alternative issue as well. Right? One of the things is that it demonstrated overfitting issues, and there's a lot of interesting overfitting issues that it was in particular the humanoid robot groups had found. Right? So here's one example. So a coworker is teaching an agent to navigate the room. The episode terminates as the agent walks out of bounds. He didn't add any penalty if the episode terminates this way. The final policy learned to be suicidal, because basically it's a robot that's trying to get to the right place, but if it does the wrong things along the way, then it loses points. But if it leaves the game area, then it suddenly just terminates the game. So what the agent learned how to do is it said, okay, if I kill myself instantly, then I will never have negative points. And so, boom, there you go. And so it basically, and so we started to learn that, if you let these learning systems try to try to build their own policies, they can start to find these very adversarial effects, which you really don't want to happen. And so, this really became an issue when you started to look at a lot of things going on with self-driving cars and self-driving airplanes, because these policies of, what if I just drive over one squirrel, I guess that's better than a baby, these things actually started to be, found and actually a part of what is driving cars. And this is the issue that is starting to become, that was becoming present in our society, right? So, there's this overfitting issue that became even apparent even when it was just doing things like playing little video games, because it could find adversarial kind of solutions. But the other thing that started to come up as well was we started to learn what the real cost of all these things were. So I'm just, there's some open data. Now, some of these numbers are a bit approximate because not all of these numbers are open, but there's a lot of speculation has these numbers, so I put one source there that has some of these perspective numbers, but there's also some hand-wavy around like, oh, so-and-so estimated this using the power output of this power plant, yada, yada, yada. So take these numbers for a little bit of a grain of salt, right? But you can see that as the complexity of the system grew, there's an exponential cost growth, right? So for example, in order to train a bot in order to play Go, it costs $35 million, which, okay, if you're a PhD student, that's a lot of money. If you're Google, Google's like, that's a little bit of money for a bit of PR, right? GPT-3, so the natural language processing system that we said was not good enough to truly use in practice, that was $10 million, right? When you start to get to Alpha Star, it was about $12 million of research for the final run, but about $1 billion to be able to do all the training that was going on in the game in the first place, right? So about $1 billion to make it play a game of StarCraft, where then in the last game, one of the pro players found out how to make it do the wrong thing. So that's a good use of $1 billion. And GPT-5, the actual training cost was about $500 million, but that's actually just them clicking the button and the power to run the compute of the system. The estimated cost for GPT-5 was in the tens of billions of dollars, right? So you can see the evolution of this, right? You have, the GPT-3 era was about 10 million, and then you had an era of about 100 million to 1 billion, and now we're in the era of tens of billions, right? And so when people are starting to say, GPT-6, ChatGPT version 6 is going to come, and it's going to be, a little bit better, right? Remember, the difference between ChatGPT version 4 and version 5, it's a slight improvement, right? The next one is going to also be a slight improvement, but looking at the way that this is growing, it went from $1 billion to train version 4 to tens of billions for version 5. We're looking at hundreds of billions for version 6, right? And this tells us that, even though we might be scared about how these things are evolving, really, if they have to 10x the amount of in order to be able to evolve each time for this little tiny improvement, how many more 10x's in dollars is there really going to be left, right? We really should be questioning how much better they will get from the state that they are right now, because they're really starting to hit a limit here. And so, this is just some more quotes about this. So, for example, one of the things that's happening right now in the United States is that Pennsylvania's dormant 3 Mile Island is actually, it's an old nuclear power plant, was actually bought by Microsoft to be able to be turned back on because they need to have a new power source for their new data center for the new training, right? So we're talking about like, we need, the next training is probably going to take on the order of hundreds of billions of dollars. Literally, these companies are requiring to buy and build new nuclear power plants in order to make this happen, right? So this is not just perspective like, willy-nilly, it might cost that. They're literally already putting the hundreds of billions of dollars in to build out the infrastructure here, right? So they said, again, Sam Altman said that the GPT-4 was in the 100 million range. They said the 2025 model was in the $10 billion range. So that was GPT-5, right? And then so GPT-6, they're saying that they're going to 10x this again, 10x this again. And so we're really looking at something where we're talking about, the Stargate project, which is the next one that's coming from OpenAI, the one that's being built down in Argentina. They're talking about their next one being a $500 billion training project, right? So while what I will show you a bit later and how all this automated coding techniques actually work, and again, you should start to be using them today, there is something that you should be thinking about in the back of your mind being how much more will they actually scale, because this is how the costs are truly scaling, right? So, if you think that they're going to get perfect, I will question whether you think, whether there's going to be the next doubling going on in this space. So what this really kind of talks about then, what I'm really trying to hit on then is that, we've been building on this idea of the bitter lesson of AI. And the thing behind it is, what we have learned is that over time, if you just have a general method where you only try to work on a general method that scales with compute, this outcompetes everything in the long run, right? And this kind of worked for the first 6 decades of AI research. But we're starting to hit a point in the scaling where you say, okay, in order for us to scale more, we're going to need to, build new nuclear power plants. We're going to have to create nuclear fusion. We're going to have to build a Dyson sphere around the sun. Like, we're hitting a level of scaling where it just does not even make sense for the amount of energy that the human race creates, right? So it's no longer something where you just say, hey, let me build a bigger computer. Now it's, hey, let me try to get all of the power of the entire country of Denmark, and then that's the only way I can train the next version of my system. But my scalable general system will be better if you give me all this power, right? We're starting to hit the edge of where the bitter lesson of AI actually starts to work. So if this is the case, then where do humans play, or what is the next thing that's going to be going on in this space, right? So with ML and AI scaling costs growing exponentially, is there a right way around these issues, right? This is the thing that we should start to ask. Is there a way for us to be able to maybe change the thesis a little bit, or change the way we work with these systems such that we can still get the next doubling, the next order of magnitude increase in productivity, with the fact that we know that these techniques are kind of leveling off in how good they're getting, or they will at least take, another 100 billion, 1 trillion to get the next tiny improvement, right? And this is where we start to look at these new methods, right? So, again, this is a hand-wavy kind of plot here, right? But this is where the talk is really focusing on, this purple line, which is these methods for scientific machine learning and agentic AI, right? What these methods are really starting to look at is, given that we have these scalable general methods, right? Given that we have methods for training neural networks, given that we have methods for agentic AI, what are the techniques in scientific computing and in the way that we do mathematical modeling that incorporates these as a central element to be able to accelerate how we do science, but does not rely on them to solve the entire problem, right? And this is where we're starting to look at, okay, if you use these methods, so let's say if you use everything machine learning has to give you, you're going to at least do as good as machine learning. But maybe we can do a bit better, because maybe we can fill in those gaps that the AI and machine learning techniques could not do in the world of finite data, finite money, finite power, right? And so there's really kind of 2 solutions then kind of going forward that we're really looking at. One is the space of scientific machine learning. The other is agentic AI. And so how do we kind of think about what these 2 things are? The piece of scientific machine learning is adding scientific models, or adding scientific knowledge to scalable AI methods, right? And we'll go into very deep depth about this. But the key idea behind this is, instead of trying to get the machine learning to learn everything, what we can do is that we can use our expert knowledge and our ideas of science, and we can augment it with scalable machine learning systems to do better than just a scalable machine learning system on its own, right? So this is one path forward that is really kind of saying, I accept everything that's going on in AI machine learning, but I'm going to now try to beat it by having me involved as well. Right? The complete other way is this agentic AI, which is to say, hey, look, there are all these systems like ChatGPT, large language models, that are trying to automate the coding approach, but how can I, as a scientist who does actually know something about my domain, how do I use these tools and how do I use this to be able to be a better scientist, right? And so the first part of the talk is going to be all about scientific machine learning, which again, I've given a version of this talk a few times before, so I'll do this one a little bit faster. But then the second part of this talk, I'm going to go into the agentic AI systems, the bot armies we've been building out for running the SIMO organization, and how we've effectively placed, a few undergrads or so with an army of 50 automated bots continuously running. And I'll show you exactly how we get this all set up, so that way everyone who's leaving the room today can also have their own bot army running. But again, that's the afternoon. That's the second part of the talk. First part of the talk will be scientific machine learning. Right. So what's the motivation behind scientific machine learning? So the motivation behind the scientific machine learning approach is twofold. One is to say that, let me make sure I keep track of time just so that way I can do all this beautifully. All right, about halfway through, exactly might be where I want to be. So the idea behind scientific machine learning is that when we do all these AI machine learning methods, we say, if I have enough data, then I'll be able to make good predictions, right? So you say, oh, if I have, here is showing some biological data, but we want to be able to say, okay, if we have biological data, if we have chemical data, we have data of everything that's going on in the atmosphere, in the clouds, if I have enough of this data, then the machine learning should be able to learn from it and make good enough predictions, right? But the key insight to have is that has a very strict reliance on homogeneous data, right? Like when we say machine learning is working on data, we implicitly mean that it's on homogeneous data. What do I mean by that? Well, everyone here that's been training neural networks, right? You know that your neural network has to have the same kind of input, right? There's a number that you have to have some kind of input where you say, okay, it has to have 128 different values. All those values have to be floating point numbers. Like there's a homogeneous input that has to go into your neural networks. And it turns out that is not all the data that we have in science, right? I think a very good example of non-homogeneous data that is captured in scientific knowledge is how do we know about general relativity, right? So everyone here probably knows what general relativity is, even if you don't work in that area of physics, right? And everyone here probably knows at least something from watching Cosmos or some Netflix documentary about how we know how general relativity is true, right? Now the thing is, there is no machine learning level data set that could train an AI general relativity. Because the way that we know about general relativity is true is actually a few different facts, right? One of them is Thomas Eddington's experiment, where when there's a solar eclipse, you can actually see the stars move, right? There's gravitational lensing. We've seen gravitational lensing in other cases as well. One other major prediction is the perihedron of Mercury, right, which is one example that I'll be able to show you in simulations. Right, the orbit of Mercury is not circular; it ends up being a Lissajy pattern, and that's one direct prediction of general relativity. Another reason why we know this is if you try to run the GPS satellites, right, you have to take into account time dilation. So I know a lot of people here that work on with satellite data actually have to take into account relativistic corrections, right? And from all these pieces of data, we know those equations of general relativity must be true. But there is no single trillion gigabyte data set that tells us everything about general relativity is true, that follows one format that we can put into a neural network that has the same number of inputs, that has the same, that isn't what's generally true about science, right? We have heterogeneous data. We have different experiments that all combine to give us one scientific theory. And that is exactly the kind of thing that machine learning cannot deal with, right? Neural networks need homogeneous data to train on, which is not what we have in scientific experiments. And so what we can start to do is we can start to say, we have scientific models, right? So here's, for example, a scientific model, say a biological system or some chemical system, where someone did one experiment to be able to say, hey, look, I know that this chemical and this chemical interact with each other because I put it in a vat, right? And I actually showed that these chemicals work together. And someone else did a molecular dynamics experiment and showed, hey, look, these two chemicals bind to each other. So I know that this arrow is true. And then someone else did another experiment and showed that this arrow. And after building out a scientific literature over 20 decades, we're able to say, hey, look, this is how this area of the biological organism, this is how the chemical reactions work, right? There's no single data set that we can point to, then train an AI agent or some machine learning to be able to incorporate this. But this is scientific knowledge that we've gathered, right? And now, while I talk about this in the area of biological systems, this happens all the time in other systems as well, right? I mean, this is how we know about cloud dynamics, right? We don't have. For the dynamics of clouds, for the dynamics of plankton in our climate models, right? We don't have a single data set where we just say, hey, look, this data set has been tracking everything for so long, and this tells us everything about how plankton works, right? You do have that data set. It tells you a little bit about plankton, but then someone else actually takes plankton out of the ocean, plays with it, and writes a piece of paper that says, oh, hey, look, here's a chemical interaction that you could take into account. You have all these hundreds of papers, and then the climate model has a human that takes all of these different experiments and puts them into a scientific model, and that model is what gets incorporated into your climate models, right? And so now what we need to think about is, how do we pair these two approaches, right? How do we pair the approach that says, I can learn everything from data, and this is something that we need to take into account, it's the future because it really works well, but there are certain things that we cannot get those levels of data sets. We will not get that size of data set, but a human will be able to synthesize it from homogeneous data sources, right? So how do we pair these two things together? And the core point here is that we're going to see is that the more structure, the more model that we can incorporate into these tools, then the less data that we'll actually need for the machine learning system to work. And so, if we can pour more science into our predictor, then we can pour less machine learning in and get just as good a prediction. So the overall idea, you might be like, okay, that sounds exactly what I want to do. But how the heck do I do this, right? What is the actual mathematical technique to go there, right? And this is what we've been developing a lot as the Scientific Machine Learning Organization and the Julia Lab, right? So you can read the original preprint and everything on the universal differential equations. The core idea is this, right? I think that this is whiteboard mode right here. Alrighty. And we got this in the camera? All right. Okay, All right, cool. So let's actually start to look at this, right? So one of the things that people know about is, say, the Lock-Voltaire equations, right? And so let me kind of give you a little bit about where these equations come from. So you have a group of bunnies out there, right? So you say x prime is equal to the number of bunnies, right? And if you look out in nature, you just say, okay, if I have a bunch of bunnies, if I have some bunnies in a room, what tends to happen is you get more bunnies over time, right? They just tend to multiply. But we say that they multiply because, every 2 bunnies can create a new bunny, right? And so if you have more bunnies, they have more bunnies that are created, right? The rate of growth of bunnies is actually proportional to the amount of bunnies, right? And so you say x prime is equal to, alpha times x, right? The growth rate in the number of bunnies that there are is proportional to the number of bunnies that there are times some growth rate factor, right? Don't know what the growth rate factor is, but this is where this model comes from, right? And then the other thing that happens, though, is if you have wolves, y prime is equal to minus delta y. If you put a whole bunch of wolves in a room, right, these are carnivores. They need to eat other animals in order to survive. And so what are they going to eat? Well, the wolves will eat other wolves, and the amount of wolves that are hungry is proportional to the number of wolves that there are. So over time, you have a decrease in the number of wolves in your room, when it decreases faster for the more wolves there are, right? So these are very simple differential equations. You have the number of bunnies that you have grows exponentially. The number of wolves that you have decreases exponentially, right? Now the thing that happens is to say, okay, well, what if I put bunnies and wolves in the same room, right? Well, see, here's the thing. What happens is the wolves, they actually prefer to eat the bunnies, right? So if there's a lot of bunnies, right? So if there's a lot of bunnies and there's very few wolves, what will happen is that the wolves will eat the bunnies, right? Or The wolves will eat the bunnies. But then you'll get more wolves over time. But what happens is if there's too many wolves and there's not very many bunnies, the wolves will start to starve to death because there won't be any wolves left, right? And so what happens is you have this oscillating behavior where the number of bunnies and wolves goes up and down, right? But even though we know that this is going to be happening in practice, the real question is, how do I modify my system, right? How do I modify my system so that way I can have some differential equation where I say there's some function of bunnies and wolves, and there's some function of bunnies and wolves that completes the model and tells me this is how the system grows, right? And now, while you can sit there, you can kind of derive a system or whatnot, what I'm going to show you is this idea of, well, it was very easy for me to give you this background. It's very easy for me to tell you these equations must be true, right, in isolation. But how do we find the more difficult equations, and can we do that automatically, right? So this is really the idea behind the technique of the universal differential equations. What we're going to do is we're going to use this scalable, learnable method, right? This method that's able to learn from data, this neural network object. And we're going to say, instead of trying to write down the whole set of equations, what we'll do is we'll write down every single equation that we know. And then for the equations that we don't know, what we're going to do is we're going to represent them by a neural network. And we're going to train the neural network to answer the question, what function goes here that completes the system to match the data? So this gives us a way so that way everything that we know about in our scientific domain, whether it's rabbits and wolves, or everything that we know about a climate model, everything that we know about chemistry, we're able to incorporate this all into the same way that we build models before, ordinary differential equations, partial differential equations, stochastic differential equations. But we use a neural network to be able to capture the functions that we don't know how to write down in the system, and then we use that to be able to generate the missing equations. Basically, the way that, when you go to Google and you type in autocomplete and then you tab, and it's able to figure out what the rest of the sentence is for you, or basically you're going to do that for the scientific modeling process, right? And the way that it looks like this. This might be a little bit complicated, but again, when I do this in a step-by-step way, it'll make much more sense. So I'm going to go straight to the step-by-step way. All right. So the step-by-step way is like this. First of all, so the test case that we're going to be looking at here is early on in the pandemic in the Wuhan region, right? Early on in the COVID-19 pandemic, let's say we had 21 days worth of data. So from 0 to 21 days, we want to be able to make a prediction about what the pandemic is going to look like after 21 days, right? So this is our challenge. We have the first 21 days of the COVID-19 pandemic, and we're trying to say whether a pandemic is going to take off or whether it's going to die out, right? And so the one thing that you might want to do is, as a baseline, what happens if we use just pure machine learning in this scenario, right? Just to see what happens. So what we're going to do is we're going to say U prime is equal to a neural network, right? So this is what we call the neural ODE. This is the version that is just saying, let me learn whatever function machine learning wants to say for the growth rate, and let me use this, right? What you see is these ideas, these issues of machine learning. You see it immediately pop up in this example, right? So we train this machine learning model from 0 to 21 days worth of data, and it says, hey, look, this is a perfect fit to our data. And then we ask it, well, what's going to happen for the pandemic in the future? And it says, you basically have no pandemic that's going to happen, right? And then a lot of people will throw out these platitudes, and they'll say this is because machine learning can't extrapolate, but all of that stuff is actually meaningless kind of bullshit, right? So what really is happening here? Well, what's happening here is that machine learning does exactly what we told it to do, right? What we said is, U prime is equal to neural network. So we say, find any possible ODE that fits our data, and then continue solving that ODE past the time that we trained it on, right? And if you actually look at it, it found an ODE that fit our data, right? It found an ODE that fit our data, and it continued and extrapolated just fine. So the problem with machine learning going outside of data, extrapolating everything, is not actually some high-level thing that you just say, oh, machine learning can't extrapolate. What's actually going on is that machine learning is learning from our data set, and it's finding a function that works perfectly fine. It's the wrong function, right? Because there are many functions that fit the data at the beginning here, right? There's an exponential function, there's a line, there's a quadratic function. There's many functions. For when you just have the little tiny tail here, there's many functions that work. And what machine learning did is it picked one randomly out of the hat, and then it just said, okay, I'm going to extrapolate with that one, right? So the issue is not necessarily that machine learning doesn't extrapolate. It's that if you don't have enough data, there are way too many functions that are able to fit your data. And so, and if you want to make this thing work out, you need to make it so there are less functions that are able to fit your data. And as scientists, we do this naturally, right? How do we constrain the functions that we allow our models to be? Well, what we start to do is we start to impose assumptions that we know must be true, right? So what are some things that must be true about these types of epidemic models, right? Well, one thing that should be true is that the number of people who are susceptible, plus infected, plus recovered from the disease, plus died, should all be equal to a constant, right? You don't have people just magically disappear. There's nothing about this model, and there's nothing about the machine learning that I put in there that actually says that this conservation law has to be true. So, in fact, it's actually violating conservation laws in its predictions. So this is one thing to know, like, okay, machine learning is going, it's able to pull from any possible function, but what if we can make it be possible functions that have, this conservation law be true? What's another thing that's going wrong here? Well, another thing that's going wrong here is that the number of people who are susceptible to disease, I didn't plot it here, the number of people who are susceptible to the disease early on in the pandemic should always be decreasing, because if there was no one who had the disease before, more people were susceptible, but then as people get the disease, you have less people susceptible, right? So S prime better be negative. That's actually not true in the version that machine learning came up with, right? And so there's all these different pieces of information which we know should be true, but are not incorporated in just machine learning on its own. So if I wanted to force machine learning to go down the direction so that way it would only be able to learn in a way that matches my scientific predilections, how could I force it to be able to work in a way that matches what I know about the world, right? Well, it turns out that we do have a technique to be able to do this, right? So when you actually teach people how to do mathematical modeling, you're not necessarily just teaching someone how to build equations and you just go, oh, this is equations that people built before, right? When you teach someone how to do mathematical modeling, what you're actually teaching them is a two-step process, right? How do you write and solve differential equations, but also how do you figure out what the phenomenological properties of those differential equations are to figure out if your equations make any sense at all. Right? And that second piece is actually the core here, right? Because when you write down a set of differential equations, right? When I wrote down this set of equations for the Lockwood-Terry equations, I said, oh, there's exponential growth in the number of bunnies. And you go, well, but the number of bunnies cannot go above 100 trillion, right? And so you say, okay, well, you have to modify the equations so that way there needs to be a decay term, so that way if it gets large enough, it'll level off, right? And so when you start to talk about this world of how you do mathematical modeling, you implicitly are not talking necessarily about the equations. You're talking about phenomenological guarantees that will come from writing down mathematical equations, right? So if we want to make our machine learning satisfy phenomenological guarantees that we know how to assume, well, then maybe the way that we can do this is by bringing our machine learning into the way that we do mathematical modeling, right? And so let me do this by example. So now, instead of trying to predict where the pandemic will be predicting where the pandemic will be in 2 weeks by using that data in just a pure machine learning model, now what I'm going to do is say, hey, look, here's an SEIRD model, right? So in the pandemic, you probably heard way too many SIR models, right? This is this type of model. But the key thing behind this type of model, though, is not necessarily that here's the thing, right? So here's an SEIRD model. Susceptible individuals become exposed become infected become, they either recover or they do whatever D is, right? And so the key thing about this kind of model, though, is that there's one part that we don't know how to model well, which is exposure. How do you get exposed to COVID-19 was something that's really difficult, because if you were in the lockdowns in China, you're experiencing a very different exposure function than if you're in the no lockdown situation of Sweden, for example, right? So I don't necessarily know how to write an equation that goes right here, because it's way too, different country to country and all these things. But I do know that this type of model throws me in the right direction for machine learning. And you can see instantly from this that, training from 0 to 21 days worth of data, the machine learning is able to capture and get something that's almost correct for almost 2 weeks in the future, right? Again, same amount of data, but what I'm doing here is I'm saying, instead of learning everything just from the data, what I'm saying is, now take a structured equation where you say this is something like an epidemic model, but now learn a missing portion of the epidemic model, and boom, now it's able to start making these predictions, right? So one way you can justify what's going on here is I have put all of my knowledge of epidemics into the system, and I've added machine learning to that, and now machine learning has done better than machine learning on its own. There's also another more mathematical way to be able to look at this, though, right? So, for example, if you look at the equations here, well, first of all, S prime This is if all these, this is a positive. So let's assume that the neural network output is always positive because you can always take its absolute value, right? So if the neural network output is always positive, then you have a negative, negative, negative. So f prime is actually always negative. So remember that assumption that I said, oh, machine learning doesn't impose this. Well, now for any possible neural network that is learned, it's always going to have that s prime is negative. It's monotonically decreasing. So boom, I put one of my assumptions naturally in. One of my assumptions that I knew needed to be true about the system is naturally imposed by putting it into the mathematical modeling form, right? Now, what's another thing? Conservation laws, right? Well, if you look at the differential equations, you have minus this term plus this term, minus this term plus this term, minus this term minus this, I actually have a mistake here, it should be plus that same term, minus this term plus this term, minus this term, da da da. So because of what we know about differential equations, s plus e plus I plus r plus d is actually equal to a constant. So we have conservation laws actually imposed in the system, right? Again, for any possible neural network, it always has to satisfy that s is monotonically decreasing, that you have conservation laws of s plus e plus I plus r plus d is always equal to a constant. What else do we have here? Well, you can actually prove that this model will always have, again, for any possible neural network, it's going to have at least one peak. The reason why it has one peak is because s is monotonically decreasing, e is first increasing, and then it's decreasing. So therefore, by the mean value theorem, there must be a point where e prime is leveled off. So therefore, there's at least one peak in this model for the number of people who are exposed, and there's also one peak in the model for the number of people who are infected. So what we're effectively, so you can say, oh, I imposed, my epidemic background, and I put that with machine learning, and that made this predict better, right? A bit of a wishy-washy way, but it's one way you can understand why this worked. Another way that you can understand that this worked is to say, machine learning is able to learn any possible function, and if you let it learn any possible function, it might learn the wrong function and try to extrapolate with that. But instead of saying you can learn any possible function, if I put it into the context of a scientific model, if I say, learn any possible function that goes here, well, every possible function that goes right there in the mathematical model makes the prediction still satisfy conservation laws because of the differential equation's results. It still requires that S prime is decreasing. It requires that there's a peak in the infections. It has all these properties naturally imposed because of the mathematical model structure around it. And so we now have found a way to force machine learning to only pull functions from the realizable set of functions that we know to be true about epidemics. And when it does that, it tends to give you better results on average. I think that, as a mathematician, that is a much more satisfying way for me to understand why this type of approach would work out. And then the last thing that you can do here is you can say, well, instead of just leaving it as a neural network, what I can do is I can have it spit out what the equations actually are. And so, again, it's like truly auto-completing the model where you write down all the science that you know, you use the data, you use a sparse regression on the neural network, and then it spits out that this is the actual set of equations that I found, and it actually gives us two pieces here. One of the nice things about this is that when you actually decrease the generalization of the neural network, you actually increase the generalizability of the predictions. It tends to extrapolate better. There's some things that we're trying to prove along these lines. If anyone wants a nice PhD thesis, there's a nice way that we can probably do this proof by using properties of extrapolation of high-order polynomials versus low-order polynomials, but that proof isn't done yet. So it's a great project for anyone who's out there and looking for a reason to join the lab. Right? Second thing as well, though, is that it can actually make scientific predictions. So we allowed this neural network here to be a function of S, so susceptible individuals, I, the number of individuals who are infected, and the number of individuals who died. D, right? Now, one of the interesting things that comes out of the predictions of the equation right there is it basically just says that the number of people who have died is not, or the function for the number of people who are being exposed to COVID-19, it ends up, we allowed it to learn any possible function of S, I, and D, but the equation that it comes up with is not a function of D, which you can basically read it off as a phenomenological prediction that people who are dead are not spreading the disease, which, I mean, most people would probably think, okay, that makes sense. And, but this shows you that, you can learn these kind of hypotheses directly from this approach, right? So so this is the high-level approach, and there's a lot more to be said here. I think I'm going to be running into time limits. So what I'm going to do here is I'm going to switch from saying like, okay, there's a lot more examples I could show in terms of gravitational wave data and using this on race cars and yada yada, right? In fact, we actually worked with the women's Formula One team with George Russell and y'all. But instead of doing all that, what I want to do now is I want to switch over to doing a semi-live demonstration of how this actually works in practice, right? So here what I want to do is I want to do the Lockwood-Volterra example, and I want to show you all the code behind it, right? So what we want to do here is we want to say, okay, here's the Lockwood-Volterra equations for predator-prey dynamics, right? And in this case, we're going to start with a known truth, right? So I'm going to tell you right now, these are the equations. I'm going to generate data from these equations. I'm going to assume I only know half of the equations, and I'm going to use the scientific machine learning method to recover what the other half of the equations are directly from the data, right? So this is the set of ODEs I want to start with, and what I'm going to do here is I'm going to pull in all of these really nice Julia packages, right? In a longer version of the talk, we can go through how this all works. In fact, if you want to learn how all this works in general, you search for the high-performance scientific modeling with Julia and SciML. This is a set a workshop set. You can also find this as the Julia Modeling Workshop, which has Pluto notebooks that goes through how to do all of the scientific modeling yourself, plus the machine learning aspects to be able to automatically recover the equations, right? But I'm just going to the final notebook here on the scientific machine learning part, right? So what we want to do then is say, okay, let's generate the training data. So how we generate the training data is we're going to write down the ODE inside of the Julia ordinary differential equation solver form, right? So we write down the ODE, and we're going to then do this for a time span from 0 to 5, and we're going to solve it, right? So this is a data set where, again, this is a data set of, we know exactly the ordinary differential equations that generates this data set because we're just putting the equations into the differential equation solver, solving the equations, and getting a time series out from the ODE solver, right? And so and then I'll show a plot of this. So here's the actual ODE solution, and then those red dots are the data points around it. You can see that there's a little bit of noise around it. You know, I didn't want it to make a very simple version of this, so there's not very much noise. But here's our data, right? So we have the red dots, and we have and the red dots is all of our data, right? So what we want to do is we want to build out this kind of hybrid model, and we want to learn missing equations from an ordinary differential equation system, right? So how do we do this? Well, what we're going to do is we're going to first define a neural network. So we're going to use Lux here to define a neural network. This is just, you know, if you go to the machine learning libraries, you see that you have to have an activation function. We chose the RBF. It can be pretty arbitrary as to why it's an RBF, et cetera, et cetera. That's the question for another day. But basically, we have a neural network, a small neural network. In fact, you can see that this is a pretty tiny neural network, the hidden layer sizes being 5. So in the grand scheme of, you know, when I'm talking about, oh, you know, people are doing these, you know, trillion-dollar, you know, multi-GPU kind of neural networks, they're talking about hidden layers of, you know, size 1 trillion or so. We have 3 hidden layers of size 5, right? So this will run on your laptop in a few seconds. Very different scale, but again, the reason why we're able to get away with this is because we're replacing a lot of the work of machine learning with expert knowledge and augmenting it with just a little bit of machine learning. So you can see right here, it already shows you just a little bit of machine learning is what's being augmented with what we're doing, right? And so what we're going to do now is we're going to say, okay, let's write down our hybrid model, and let's actually look at this, right? So what we're doing right here is we're saying, okay, there's a dynamical model that we have, right? There's some ODE. And the way that I define this ODE is you first get a prediction out from the neural network, right? So the neural network is predicting 2 values, right? And what we're going to do then is we're going to say that, you know, the derivative of x is equal to some known parameter times x1, or, you know, times x. So this is basically saying, you know, derivative of the first value, so x prime is equal to some known parameter times x, right? So x prime is equal to some known parameter times x plus whatever comes out of the neural network, right? Because again, this is any possible function. This is the output of any possible function. And then y prime is equal to minus a known parameter times y plus anything that comes out of the neural network, right? So here we've basically encoded this what I wrote on the board here, right? Where we say, this is an encoding of our idea of, I know this equation, add something to it. I know this equation, add something to it. Where the something is the output of the neural network, right? Now for an untrained neural network, it's, you know, this something random is going to come out of here, right? But what we want to do is we want to do the training of the neural network. When we train the neural network, then this will actually be the correct function. And then what we'll be able to do is pull that out and actually figure out what function did it learn. So let's see how this ends up going. right? So then what we do is we make this prediction function where you say, okay, you give me neural network parameters, so it's just basically a list of neural network parameters. It takes in neural network parameters, and it runs this differential equation. So it solves this differential equation with the neural network inside of there, and it gets some time series, right? But normally that time series is going to be wrong, right? Until the neural network has the right parameters, that time series is going to give you garbage, right? So what you have to do is you have to train this model. And how do you train this model? You build a loss function. This loss function is say, okay, take in neural network parameters, theta, run the prediction in order to get a time series for what x is like. And the difference between the time series that you're spitting out from that model to the data set, that should be going to 0, right? And we want to minimize this cost function. So we want to make the time series that's being predicted by what's coming out of that model be as close to the data that we have in our data set. That's all that's essentially saying there, right? So it's basically saying, there's some random f, there's some random g, we've added some random functions now to our differential equation, and just keep on changing those functions around until you find the ones where solving the differential equation with those random functions augmented to it ends up giving you the solution that matches our data set. And then there's all these little details that is on top of that, yada yada, for how you actually do the process. Again, a longer version of this workshop walks through every single line of code, but I'm trying to stick within the 5 minutes left time frame here. But when you do the training here, what you see is that, again, at the start, the predictions are not anywhere close, right? At the start, the predictions are not anywhere close. In fact, they're 1 times 10 to the 7th off, right? So adding a random neural network to your equations, especially with ordinary differential equations, you end up getting a solution that's just way, way, way off, right? But what it starts to do is starts to find better and better neural network parameters, be able to hone in on how exactly this behavior is, until by the end of it, it's able to give you something that's a very good approximation to your system, right? So again, the first loss, so the first time series difference is all the way up in 1 times 10 to the 7th. But by the end of this training process, it gets down to something where the difference between the time series it's spitting out and the time series and the original time series of the data is the summation over the whole thing is 1 times 10 to the minus 2 or 1 times 10 to the minus 3. Now, again, I'm going fast over this portion because I'm just going to say how the training process works. This is the graduate course, 18337, the math course at MIT. We spend months and months and months going exactly how the math of this works. But if you use the software, you basically just say, build an optimization problem, click solve, and then will spit you out effectively the neural network parameters that makes the training process solve, right? So we'll skip over that big training part just to say that's where all the actual math is, right? But when you do that, let's actually see what we get, right? What you get is here's the prediction then for the learned. Once we have the learned neural network parameters, this is what it's predicting the output of the ODE would be for the prey and for the output for the predator, right? And you can see that it's effectively found what the missing f function is and what the missing g function is. Right? Now, but it's only representing it as a neural network. So as a neural network, what we can do, though, is we can put values in, and it spits values out. What those values are is effectively the missing parts of our differential equation. It's basically what is the amount that our x prime and our y prime values were incorrect, right? And now, but it's not really that useful. So what we want to do next is you want to say, now that you've actually found a computable element that tells me the value off by which my original model was, can I convert that neural network representation to a human readable representation for what I was missing in the model, right? And so what I'm going to do, this is that next part then, which is a symbolic regression aspect. So what we do then is we say, okay, what we actually have here is we have a function of x and y that we can spit in. So what I'm going to do now is I'm going to take a bunch of values of x and y. So I'm going to take a bunch of values of x and y. I'm going to put them into there, and I'm going to build a data set that's going to be x and y goes in, and f of xy comes out. I'm going to have a data set of inputs to outputs, inputs to outputs. And I'm going to now pull this out of the system and say, there's no more differential equation. Now let me learn just in isolation this mapping from xy to f of xy. And so again, the details, all the details are covered in the code. And you have to be, in order to run this method, you need to give it some basis in order to be able to learn from. And we're going to say, well, from the set of all polynomials up to order 4, find the simplest version of the polynomials that is able to then satisfy what is the function that represents the neural network training. Right? So you can see this is the polynomial basis that we're then pulling from. Again, going quite fast over here because each one of these could be a 2-hour lecture for how each of these steps works. But then we're basically going to run this, and then I want to show you two things. Right? So the main element that I've been trying to tell you here is that scientific machine learning, this idea of putting expert knowledge in, is able to improve on what doing machine learning on its own is able to do, right? So one question that you should have with this example is, if I tried to just make the machine learning learn all of the equations itself, how well does it do, right? And we actually have this answer inside of the notebook. It says right here, so if you were to give machine learning the ability to try to learn all of the equations, here's the equations that it comes up with. It finds that the equations are best linear in U1, best linear in U2, best linear in U2, right? If you go up to your original equations, you can see, if U1 is X and U2 is Y, it didn't even get close because it needs to have a quadratic term here, it needs to have a quadratic term here. In fact, for this type of mathematical model, you cannot have this kind of behavior, this kind of oscillation, which is not just a circle, without having a quadratic term. Like, it's actually impossible with a linear ODE model. And so you can actually see from this right here that if you just did this process without the prior scientific knowledge, if you did the model without this prior scientific knowledge, then it gives you out this prediction, and therefore it didn't work, right? Now, is this to say the machine learning can't work? No, the problem is that we had a very small data set, and you need a huge data set for machine learning techniques to work, right? So this shows you that if you just learn the equations for me, this doesn't work. But what if we had this process, right? So when we train the neural network to just learn the missing equations, if we now perform the symbolic regression just to learn what the missing equations are from this data, what does it come up with? And you can see from this, you get that you're missing this term, quadratic term, and you're missing this term, quadratic term, which is exactly what we expected, right? Because remember, what we did in this example is we presupposed that you knew this term, and so the missing terms were constant times xy, and the other missing term was constant times xy, and that's exactly what the machine learning was able to come up with, right? It was able to show you that, say, hey, look, that thing that I added to your equations that completed your model is a constant p1 times xy and a constant times xy, and boom, it was able to basically find exactly the missing terms of the model. And then what we're able to do is we're able to then say, okay, now that we know the missing equations, we can throw the missing equations back into the system. And the final thing here is that, again, we only train on this tiny little data piece right here, but then we predict going forwards. The blue line is our prediction. The green dashed line is actually the data. And you can say it's very difficult to look at the difference between the two, and it's because it's pretty much a pretty exact prediction. And the reason why it's almost an exact prediction is because it's actually learned exactly the correct equations, right? There's no neural network here in the end, and once it found what the correct equations were, it's able to get a very good prediction because it's not trying to estimate these equations anymore. It's making the true extrapolation with the actual equations that it found. And so this shows you the scientific machine learning process in full. Again, there's so much more that can be said here, but this shows you that, this is one way to start to look at this space of machine learning and say, hey, look, people are doing a lot where we're learning from data. Where can I, as a scientist, be able to work in this space? Well, what I can do is I can bring everything that I know. I can bring all of the equations of a climate model. I can bring all the equations that I know of chemistry, and I can presuppose these into my model because I know it's not covered by my data, but I can use these tools as a way to be able to learn things, to learn what error was I missing in my model. How are we supposed to account for plankton if there's some event that, say, puts more oil into the ocean? How do I account for that effect in my plankton model, right? We can use the fact that these tools exist to make us better at building models quicker that are more accurate. And so that is the first thing I wanted to capture. Where do humans go in the age of AI and machine learning? This is one way that we can be incorporating it. The next way we can be incorporating it, though, is with agentic AI. And I think that then will come after the break because we're supposed to have a break right now. Yeah, but I will take questions. Yep. All right. I can run.
You have to share.
Oh, I can use the other mic. Yeah. I can be constrained.
Thank you, Chris. It was a great talk.
Look, I'm going to ask you a question as a physicist, okay? So I was learning. My mind was going. Okay, imagine you had, going back to the 19th centuries. Imagine that you had Faraday experiments.
Mm-hmm.
Could your equipment find Maxwell equations? Or if you had, say, the data from the speed of light and for instance the Lorentz equations, which is just the same as the Einstein special relativity equations. The difference is just the way space-time is understood. Would you change that axiom at a deeper level? And finally, the third question, you see it's mostly the same question, just three different aspects. If you had if you look at the cosmological data, could you guess if it was general relativity or some other approach to general relativity, like myriads of physicists have tried, and can you distinguish if one is better than the other by looking at all the different types of differential equations and tensor equations that can happen? Thank you.
Yeah, very, very good question. This actually comes to some of the things that we've been working on with some collaborators. Again, this is not quite in the climate space, but one of the things you can go to is if you go to docs.sciml.ai, you go to our showcase, right? In the showcase, you'll find automated model discovery. You'll find discovering relativistic corrections of black hole dynamics. This is actually an example where we say, okay, and this is done by one of our collaborators in a published paper, so you can read the paper and whatnot. But we turn their paper into a documentation example at this point, where what you do is you say, okay, assume that you only knew Newtonian physics, right? Assume that you only knew Newtonian physics. So you write down the two-body problem for a Newtonian system. The solution would be an ellipse, right? Now, if it's a black hole system, black holes are relatively big, right? But now if you have two black holes going around each other, then you must have relativistic corrections, right? So can we automatically learn what these relativistic corrections are from data using gravitational wave data from LIGO, right? And so this is a complete example of doing that. It's simplified how the data works so that we don't have to download data each time, yada yada. But you can basically see that it starts from a solution that is an ellipsoid, and it learns what the relativistic correction is. The relativistic correction is a small change to the equation. Right? But once you learn that small change to the equations and you extrapolate it out, well, then when you get a different orbit, and the orbit gives you the Lysygy pattern that you expect, right? There's the same thing as the Lysygy pattern of Mercury around the sun, right? And so this is exactly that kind of thing where it's just learning what is the small equation correction, and once you extrapolate out then the differential equation, it says there's actually, once you learn the small correction, you actually get a completely different phenomenological prediction from what the orbit would be. It should be the Lysygy pattern, which you can then say, okay, now let me see if I go find that pattern, and then that would be this, right? And this is actually this is actually the process for how general relativity was first proven, right? The perihelion of Mercury. So this shows you that at least something similar to it can be done with the scientific machine learning pieces, where again, a human is kind of saying, if I start with Newtonian physics, I cannot make things match the data. What is the minimal change to the equations that I can do? And then what is the long-term effect of having that minimal change to the equations, right? So I recommend you go through this example that goes through the step-by-step about how this is done. Now, when you're talking about the cosmological models, there is actually a group that's bringing this into cosmology. I think that it's called symbolts.jl. So symbolts is a symbolic numeric cosmological model which is fully created using the JuliaEO ecosystem. It has a full model of inflation and cosmology, et cetera, and it's using this with the whole modeling toolkit ecosystem in order to then be able to use the scientific machine learning to be able to figure out what are the standard assumptions of cosmology which are incorrect that need to be changed in order to make better predictions of the system. So yeah, if you're into cosmology, I'd say go check out Symbolts because people are now starting to use this in the SciML space. So I love the question because I've been helping this guy, all the last few months, and so it's really cool that I get to bring this up. It's the paper's just super cool. So.
All right, very different question, I guess. When you're ready.
Yeah, I'm ready for it. I just wanted to kind of show something on the screen while while you're talking, just kind of like back matter, doing an advertisement for somebody.
I'll wait.
Well,
Okay.
as American, we do have a lot of advertisements as you walk around everywhere, so we're used to this.
All right. So my question is about the beginning of your talk. So another thing that humanity is doing right now, I should say Silicon Valley is doing right now to crash the planet is, in addition to building data centers to train AI to make us comfortable, they also, there's the cryptocurrency business that changes the rules in a way and changes the relativity to money. And that same sort of group of people also considers that the timeline is finite, that in 20 years we are post-human, so none of this matters anymore. So I was wondering if you take this extrapolation that you had at the beginning in terms of cost, if you were to express it not in US dollars but in Bitcoin, how that looks like, and once you put a finite time horizon to it, how does it affect your thinking?
So yeah, that's a really good question. I mean, let's go back to how the numbers are evolving to just kind of get a feel for it, right? Basically what seems to happen is that there's a generation about every 2 to 3 years, and at each generation we get a small increase in AI accuracy for about the 10x in the cost, right? You go from the 10 billion range, and then there's the 100 billion range, which is mentioned, 100 million range, which is mentioned right here, right? And then what came after that was the 1 billion range and the 10 billion range. We're now entering into the next generation, which would be the 100 billion range for the training, right? Again, GPT-4 to GPT-5, most users didn't even notice the difference, right? GPT-5 to GPT-6 is going to be $100 billion to be able to do. Expected to have a very similar difference. Do we really believe that the $1 trillion range is going to be the one that kicks us over the line, and we don't have any work? Again, like if you look at how this is 10xing each time, I just can't see that. Maybe generation 10 down the line is the one that does that, but 10 generations down the line is talking about quadrillions of dollars. I don't see an economic possibility where it's able to literally do everything, right? So again, the second part of this talk will go into these systems are pretty good. How do we start to use them? But I really don't think that they're going to be doing, I don't think that they're going to be getting to even the PhD level anytime soon. I would put that the level that they're at right now, the $10 billion to $100 billion range has gotten us something where it's about as good as a competent sophomore, second-year college student, right? And so, okay, the $1 trillion range is going to get us, a competent, fourth-year undergrad. I think we can start to say, okay, the 10 trillion version where it gets you like a first-year PhD student or so, the math doesn't work out that it's going to completely replace you. It's going to replace a lot of people, right? Because the number of people who can code and know science as well as, a third-year PhD student is a very small percentage of the population. So a large portion of the population should be extremely kind of worried, right? But I do think that there's still a place for experts just because how this exponential growth in cost, when you take into account the exponential cost growth along with how the rest of AI is growing, I just can't see it actually doing the next doubling because, yeah, it's been growing. It's been going exponentially for 6 decades, but exponential growth is really hard to do for a very long time. And so we're hitting the fundamental limits here.
Okay, congratulations for your presentation. I believe that this is the way. I am a guy that understands a lot of Voltaire equations. They are very good. They are a very good example to explain.
They're my favorite ODEs. Yeah.
Yeah, they are really good because they are understood by most people, and if Plato and Aristotle they would be here. Plato would be for the equations that you are using, and Aristotle they would be just for machine learning. And because you used to say that what exists for Aristotle, what exists is what you see, and for Plato, what exists is what you understand. And so to understand, you need the equations. So I think we will talk afterwards more about this because the Lotka-Voltaire equations, they are a good example. But in fact, what we want for the prey and predator model is a more complex system of equations that are many terms like these ones with plus and minus that you have shown to cancel. But we need to have more variables. And so, is there many people working using this philosophy, or not so many? Or?
Yeah, I mean, in 2019 when we created the SIMO organization, there really wasn't a field of this at all. But now it actually is a field that has a name, right? It's the field of scientific machine learning. It still doesn't have a Wikipedia article really, but it has something that has been come along, and you can see that the scientific machine learning organization in Julia, this is the organization that I've been driving with open source software. This has been the community that we've been building. We now have about, if you look at the documentation, there's about 300,000 downloads from unique IPs every single month. So this gives you it's in the 300,000 scientists or something that are kind of using some element of these tools, downloading it every month. And so we estimate the number is about 500,000 at this point, right? So it's still a small group in comparison to a lot of things in the world, but there is a group that's saying, okay, maybe this is the approach to science that we should be doing. And there's a pretty wide community, and so you can join our chat rooms. I think that the Julia chat rooms does have 15,000 people who will respond to messages. So there's quite the activity going on. But still, even in these numbers, right? There's tens of millions of scientists in the world. 500,000 are kind of going on this route. I believe that number is going to exponentially grow to become every scientist needs to take into account these ideas. But but right now we're still kind of at the early stages. So yeah, if you look for everything that's going on in SciML, scientific machine learning, this is the language that we've been putting it out and the conferences that we've been putting on. In fact, hopefully we'll have a conference here in Terceira on SciML in about March or April as well. So yeah, it's grown from something that's just a few people at MIT to being a kind of a movement and a change in how we're thinking about science. Yeah, and it kind of go with your metaphor here. It actually made me think of a different metaphor, right? You said Plato and Aristotle, right? If you want to think about it in terms of Sith Lords, right? It's kind of like Darth Sidious is like he's like was trying to be like, the way to do all of science is that we have to control everything. We have to control all the mathematical modeling, right? Darth Vader comes in to just say, I'm going to use my passion to just learn from everything, right? But Darth Vader was only able to overthrow Sidious when he actually pulled in Sidious's methods and then put him down, right? And so he so the Sith Lord is only able to take over, be able to overcome the other Sith Lord when he incorporated their other methods. So maybe we should take that into heart as well if we want to become proper Siths.
Okay, thank you very much.
Yeah, just another quick one. Something that I'm not very familiar with, but have you heard of this Denario project? I think that's coming out of the Simons Foundation.
Yeah.
And somebody pointed me to this paper. The theme of it is that they are now using AI agents to essentially write papers from scratch. Mm-hmm. Is that something you want to comment on, or have?
Let's wait for the second part, because the second part will be on the large language model usage.
Thanks, Chris, for the wonderful presentation. I just wanted to ask, it's just the validation, differential equations as they are, you took the case of Lotka-Volterra, these are the very simplified versions at the set, it's not the actual depiction. And once you use symbolic regression, again completing the loop and generating, can this be further used? Lotka-Volterra can be used in many, like in economics also and in fire studies also. So can we use, closing this thing, can we create data which can be actually used to again retrain the machine, to retrain the machine and make the things closer to the actual scenario?
Yeah, so I'll say that the example that I showed here is kind of like the teaching example of here's an example I can show in 5 to 10 minutes and show you every bit of the code. But a lot of the true examples of this being done in the literature is now doing this with real world data on much larger equations. I think that one that I like to really point to is this one on absorption modeling. So this is one that's on modeling chemical plants. And in the chemical plant model, effectively what's done here, I guess, let me try to see if there's an open access version. Yeah, you can always find the archive version, right? And what's going on here is it's presupposing not that it knows, anything about chemical reactions, but it's composing a diffusion advection system, right? So it's like embedding a neural network inside of a partial differential equation, where it says like, okay, know that this molecule is diffusing and advecting, the other one is actually constrained to the reactor, and it's using, it's a much more difficult system, and doing this with real world data, yada yada, and it's showing that we similarly that in this kind of scenario in chemical engineering, it works out. And again, there's now thousands of citations on the paper, so there's a lot of different examples of this in different scenarios. What I would point to is if you want to look at more of these examples, there is a talk that I gave, which is let me see if I could find it easily. Accurate and efficient scientific machine learning. If you look at this talk, accurate and efficient scientific machine learning through differentiable simulation, this talk actually goes slide by slide along, showing, for example, this in aerospace engineering, this in building engineering and civil engineering. So there's a lot of different validation points there. For this version of the talk, I cut out most of the validations just to kind of go straight towards one example within a 1 hour period. But these other examples are, like instead of trying to show code, they're more trying to show the more complexity, right? So different versions of this talk give you different aspects. I recommend you check out this talk because this covers what you were looking for there.
I have one question.
I have one answer.
Okay. What SciML model would you recommend for fitting differential equation to long-term environmental data sets?
Yeah. So what I would do is I would just find, in whatever field you're in, someone has been creating differential equations, right? Someone has been modeling, so long-term environmental data sets, right? I mean, a lot of people in this room build long-term climate models and these predictive models, right? So what I would do is I would just go to, Milan over there. He has speedyweather.jl, right? And, it's like, okay, if the type of model that you need is some kind of weather model, or, okay, if you have a model of the current environment, go find the person who is actually building the model in that space. They're the expert in this, and start from their model and incorporate machine learning into the modeling that they've been doing, right? So as someone who's not necessarily in the environmental modeling space, I can't necessarily tell you who's the person to go to there, but I can guarantee you there's someone who's building mathematical models of it, and that's the person to start from. And that's the key thing about this technique, right? It's about starting from the scientific knowledge that we have. Go find the person doing the differential equations in your space, right? I know this. I know the things from my spaces, the biochemical models and such. But when you go into like certain climate models and such, go talk to the people who build out Klima and these kind of models, and then really start to ask the question of, okay, if you have a complete predictive climate model, how do I add machine learning to this, and how do I do my part to add this? The actual doing scientific machine learning in those contexts has a difficult computational and mathematical problem to actually train the neural networks and such. But if you can get beyond that part, then that's the groups to work with, right? The ones who have the most predictive models right now in the space.
Thank you for a good talk. It's really interesting to hear about this combination of science and machine learning. But I also sometimes hear about it in other contexts where it doesn't refer to like the JuliaEO community. So it seems like in Python and other places there are been taking other approaches to combining science and machine learning. What are your thoughts about some of these competing approaches and views, and how do they fit in, and what's the maturity of them?
Yeah, so that ends up being kind of a different talk, and I can show a few things there. I think that this talk has one of it. One of the things that you can see, for example, is that you do have some approaches in JAX where you say instead of trying to come up with different derivative approximations and such, maybe you can just do differentiation of the simulations. I have a talk which shows that actually that approach doesn't converge to the right answer, and provably even in very simple scenarios. So here's an example. Here's an example with JAX, just on a linear ODE. You tell it to do automatic differentiation of the linear ODE, and it gives about a 60% error. And as you send the amount of, as you send the tolerance of the solver to 0, it actually does not change the error in the gradient at all. And again, there's a talk that I give that's this. You can find it on YouTube. It's the numerical analysis of differential simulation. We also have this inside of one of the review papers. It describes exactly why some of these other approaches might not be convergent to the right answer. In fact, you can actually prove that this version, why it's not convergent to the right answer, right? So there's a lot of of the little details in the mathematics that needs to be taken into account where, if you try to just do this with general machine learning techniques, a lot of the difficulties in terms of numerical analysis, handling stiff equations and things like that, ends up making it so that way real world equations have non-convergent derivatives and non-convergent estimates. And so what we've been doing a lot in the JuliaEO space is making sure that we can have, incorporate the ideas of numerical analysis. So the same way where you just say, hey, look, one ODE solver doesn't work for all things. What are the different ways to calculate gradients and everything such that we can provably make this stuff convergent? And that, that's where the deeper math and science comes in, which I kind of cut out completely out of this talk. But you can go find the other papers and such that go into that. So when you see a lot of the software that we use and stuff, there is a lot of details as to why we do these techniques, which, again, is... If you come by MIT, go to the 18337 course, we'll go through all the proofs. So that's one piece, right? So it's why we do a lot of adjoint methods instead of just differentiable simulation, because automatic differentiation is not convergent. There's another thing that you will see sometimes, which is physics-informed neural networks. Which I'm trying to find where I have a piece that kind of shows what I wanted to show there. But the thing about physics-informed neural networks is, so we're using the idea of, if we have prior scientific knowledge, we should use all the prior scientific knowledge that we have, and then only augment what we need to with machine learning, right? The issue with going the it's right here, right? The issue with going the physics-informed machine learning physics-informed neural networks approach is it's saying that, okay, what we should do instead of trying to solve the equations with solvers that we have is we should also use the neural network to represent to do the solving process, right? So what we are doing here is we're having the neural network represent the derivative. The fundamental difference that you see in a lot of places with the neural operators in the physics-informed neural networks is they're using the neural network to represent the integral, right? I think that there's a few reasons as to why you, based as a mathematician, just go, that's got to be the wrong approach, right? One reason is because derivatives are always a simpler representation than integrals, right? In fact, for example, it's very easy to write down derivatives that don't have an integral representation, right? The integral of e to the minus x squared, the integral of a normal function does not have a function representation in elementary functions, right? And so that if you're trying to make the machine learning problem as simple as possible, you want to represent the derivative, and so that's one thing to do. The other thing is to say, if we're trying to use as much scientific knowledge as we have, one of the pieces of knowledge that we have as well is numerical analysis, right? So many people in this room have studied how do you do accurate, what is the most optimal way to calculate integrals and all these things, how do you solve differential equations, right? We can actually prove, for example, that Gaussian collocation has the fastest, is the fastest way to be able to integrate polynomials because you get higher order, yada, yada. And so if our approach has been to incorporate machine learning into the tools of numerical analysis that we know are optimal, rather than trying to have the machine learning also have to learn all the numerical tools. And what you end up getting from this difference is, for example, here's looking at the difference between, DeepXDE, right, which is the physics-informed neural network library, and PyTorch. In order to be able to learn the parameters of the Lorentz equation, it took 362 seconds in order to do the training process. This is actually just a screenshot pulled from their tutorial. When you do this with diffeq flux in this differentiable programming approach, it takes 0.03 seconds, right? We're talking about 10,000 times difference. And the reason is because if you try to say, I'm going to make the entire problem be a machine learning problem, they use really large neural networks to be able to do things that we know how to do with very simple, Runge-Kutta methods. So another thing that's kind of implicit in our approach, that's the kind of like the JuliaEO approach, is to say, let's do scientific modeling with all the tools that we have and a little bit of machine learning, right? And again, as I showed in this example here, when I say a little bit of machine learning, I really do mean, we have a very, very tiny neural network here, right? We have a neural network that has 3 hidden layers, right? 3 hidden layers of size 5 each. This is the tiniest neural network you've ever seen. So we're doing a lot of scientific approach with small neural networks. The other groups are trying to look at this as a problem of really big neural networks on GPUs and, a little bit of scientific knowledge. And you can see the difference. You can see the difference immediately when you actually look at the numbers that, it takes 10,000 times longer, it takes GPUs, and it has less extrapolation properties. And so, again, that's a different talk that I give, but there are some good things about the neural operators. In fact, if you're going to be working on very high-dimensional partial differential equations, their kinds of approaches will do better because the approaches I'm talking about here require that you already know how to write a solver for it, right? So, if you don't know how to write a solver for equations, so if you have a Volterra integral partial differential equation or something, right, then using an approach that is fully machine learning might be a better fit. If you have a 100-dimensional partial differential equation, that might be a better fit. But if you already know how to do semi-discretizations of PDEs for, climate models and such, Why not use all that information? You'll save 10,000 times in your compute. So you know, I think what ends up happening is it ends up segmenting where we end up working on very different looking problems for that reason. Where the problems that we look at is a lot in ODEs, DAEs, and partial differential equations that we know how to do discretizations with. And the more the focus then of the other SciML groups tends to be things like Schrodinger equations and hundreds of particles where there's no representation in terms of differential equations. So great question. But yeah, I could show you the other talks that goes into that in copious amounts of detail, but that's really where the difference is, that we represent derivatives and use solvers, they represent integrals and use the machine learning to do the solve, and there's the pros and cons of that.
For someone new to Julia and SciML, what is the best starting workflow to go from a mathematical model to a working simulation?
That is a great question. So I'd say the best starting workflow is to find the Julia modeling workshop, right? Because the Julia modeling workshop starts from how do you use Julia, you know, getting started with Julia, how do you install Julia, how do you, build arrays and matrices, how do you write down a model for a differential equation solver, and only at the very end, after teaching you everything, it then says, here's how you use scientific machine learning with it. So it's really a starting from zero to hero kind of approach. I would say that these workshop notes, these are ones that we're pretty happy with. They're kind of new as well. They're just created 4 months ago. Other thing that you can do is you just go to docs.sciml.ai. There's a getting started here, which goes all the way from the start for new user tutorials. And you can see build and run your first simulation. This shows you from the very beginning, how do you start with Julia and get started with this. And it goes all the way down to discovering general relativity, right? And all within one documentation. So again, you can start all the way from the start and go all the way down, and we have the resources. Now, if you want more resources, what I would say is there's two things to do, right? You can always go to the Julia discourse, so discourse.julialang.org. This is where you can always ask for help in a public forum. So if you're running into any issues, I get hundreds of DMs from scientists every single week about, here's my ODE, here's my data, what's going on, how to improve this, right? If you want to send an email, feel free to do. If it needs to be confidential, you can always keep the models confidential. And so this is how you can do it a bit more publicly. If you want to do it slightly less publicly, I'd say go to julialang.org, hit on community, hit right with these right here. Zulip or Slack are really great chat channels. This will get you into the chat channel. Again, there's about 15,000 people in these chat channels that can help you with, I tried to write this in my ODE solver, I got this error, what do I do? I think a lot of the people in this room probably all met each other through the Slack channels, right? And so, if you want to get started, I'd say, don't just look at this as, hey, look, here's the documentation, but there's a huge active community. Look at the documentation, but also join the community. Feel free to ask questions. We're accessible. We don't bite. In fact, I'm here on Terceira Island. If you want me to pull out my laptop, you can always find me at the Texan after karaoke, and boom, bring a laptop, and we'll between songs we can get your model working. So.
Thank you, Chris. We need to.
Yeah, I went a little bit over.
Can I ask everyone just to have a 10-minute coffee break, because we used a lot of time now, which was really interesting. So I'm guessing we're going to have even more questions after the next session. So let's quickly get to grab a coffee and come back in 10 minutes.
Thank you, Chris. Now we have a coffee break of 10 minutes.
Yeah, it's in the freaking park.
It's working just specific to nature for to do something that's not comfortable with clothes.
Yeah.
Can you send me this? Yeah, it's all the same.
Because now but the first person is doing
Yeah, and it was actually the first for me.
Okay.
So it might be second.
Yeah.
Because this was the previous one. Oh, I see. So there is a bit of an offset.
Yeah. So wait. Yeah. So you see, like this is the original one, the green one.
No, the original one's the
No, the green one.
Oh, the original one's the
So they kind of become.
Oh, area, classified exception, global notification.
Estás a fazer timesheet, já era atrasado. Era para ontem, não é? Ah, pois. Pois é.
Tu já fizeste?
Era perfeitamente tempo. Ah, então. Voltamos.
Tudo bem?
Hoje é mais. Acabamos.
Faz o quê?
Fazer uma volta.
Vou fazer uma conta, não, estou a preparar um paper para o start. Vou submeter numa conferência.
Sério?
É que nós somos sempre líderes. Imagina, fazer um artigo científico ao meio do curso, quando se quer que os resultados, é impossível, não é?
Do start?
Do start.
Mas o que é que fazes para isso?
Não, primeiro foi bom
Just a single
e neste aqui, primeiro era fazer um papel, uma fixação são coisas, são três resultados. Nem sequer uma questão de investigação por trás, não é? Pronto, portanto, a solução foi fazer uma conferência. Tive várias conferências e vais falar da metodologia. Eu vou apresentar através da metodologia. Ou seja, o quinto para aquela coisa de fazer tive um branco. Exatamente. Isso, usar o quinto, não é? Fazer da vida das residências, ou seja, falar da metodologia. Usar aquelas cinco áreas, que é a prática da economia, da política, do environment, etc. Isso já foi para a estrutura. E é mais fácil se tens uma conferência de tipo. Há muito que não tens. A revista te aceitem uma coisa destas. Eu não sei quem escreveu. Eu não sei quem escreveu. Nós somos líderes, não faz muito. Por acaso, uma dos parceiros realmente não temos uma questão de partida.
E agora? Não é que faz isto no final, não é?
Exato, mas isto não é dois. Tem que fazer uma agora no final.
Sem desenvolvimento.
da dos outros. Tem fases novas, mas depois tem a aceleração, ou seja, a implementação do mercado.
Yeah, there's one behind the globe access.
Senão, está a ver, quando eu vi, eu disse, eu pensei que fosse um filho.
Well, if you go geomarket, then you can select.
Porque não tens mesmo ideia de gerir.
For 360 comma. Yeah. And you could just.
Ah, so there's one, yeah, there's one.
That's both. Yeah, that makes sense.
No, they seem correct.
Postpone. Oh no. Someone moved.
Só por causa dos feriados. Desconto agora dos feriados. Os feriados, não é? O mês de tanto de quê? Dezembro, depois tens os feriados, depois tens aquela não é? Deram-te 26, deram-te 29.
Right, but why do they have this weird
Well, the reason is so that you basically have all the coverage over like basically you want this if you're analyzing data on like this process. Yeah, I don't know why they chopped it off at the border. Oh no, it's because it is great if care about small people and small This is only Christmas, like the whole today.
Do you want me to get you something? I noticed you didn't go there.
What?
Do you want a coffee or something?
Oh, no, I'm good. I'm good. I was there.
Oh, you were.
I don't need much. I think I'm drowning, asphyxiated. I wanna break the spell that you created. There's something beautiful, a contradiction. And you will be the death of me. Oh no, that was for those on the stream. Are we actually still streaming? Wait, what was I singing? I didn't even know what I was singing. Oh, fuck. Yep. I probably will, but I mean, this one I might be doing a lot more like live coding and stuff. But yeah, just in case. Thank you so much.
When you're ready, Chris, I think we can start.
Okay. Yeah, hold on. This is taking a multi-device kind of There we go. Perfect. All right. So now we're back for part 2. All right, so now we're back for part 2. And so for part 1, what we really looked at was the scientific machine learning, right? We looked at this problem of if we have these learnable types of methods, right? If we have these methods that can learn from data, that can learn equations and things like that, how do we use this as a scientific expert to be able to increase the speed at which we do scientific progress? And how do we use this in such a way where we can outperform the machine learning methods today by, as a baseline, using everything that they can do but adding to them, right? This is the idea behind scientific machine learning, right? So we kind of covered this. Again, we covered it really quickly. We run a whole course in this at MIT, which is like a whole semester course. So again, we really kind of just touched the surface, but hopefully we have the idea of what is the thinking behind that path, right? Now, the other path for where humans should be in the space and time of AI is in incorporating agentic AI. And I want to start to talk about this. So before I get into this, though, I'm curious, how many people here are using something like Claude Code CLI today? So yeah, it still is way less than a majority. I hope by the end of this, everyone in this room is at least set up and ready to use this, right? Because the key is that agentic AI in science is not really tomorrow, it's today. And the question is, now what I want to start with, even before I get into the more specialized tooling on this, is I want to just get everyone on the same footing to just say, how do we get started with this today? Right? Because if you're not using it today, then you're already way out of the ballpark. And I want to just get you into the space where we can start to talk about how we're improving it. But in order to get there, we got to get everyone understanding what this is, right? So just to kind of look at this, AI for software engineering has really been progressing fast. Now, again, there are some reasons to believe that it's probably plateauing because the difference that we're getting now. The difference that we're getting now between like the 2025 models versus the 2023 models and such, we're getting small percentage points improvements inside of the very basic software engineering benchmarks, right? So at a certain point, I would say that a lot of these tools, the best of these tools, are about at the level of a second-year undergrad, a competent second-year undergrad. But what you'll see is that having one of those around at your fingertips can be quite useful, even if that's where they seem to be plateauing, right? So we'll be talking specifically about these models like Gemini 3, Claude 4.5, and Claude 4 Opus. This is missing Claude 4.5 Opus, which will be the main one. But these seem to be the main models where anything below that, like ChatGPT 5, don't tend to do as well in this space, right? So hold on, the shoes are getting in the way. So why agentic AI actually works? So you might have, everyone at this point has probably played around with ChatGPT, right? And so if you played around with ChatGPT and you've asked it some questions, it probably got something very wrong, right? And so you're going to ask this question of, okay, why would I trust this with the code that I am writing, right? The real thing to understand for why this actually works is to understand why the agentic systems are different than just using the LLMs on their own. The real key thing is that they have a loop here, right? And this loop is write, execute, read, and fix, right? What I mean by this is, what you'll see is going on with these tools is that they'll write code, they'll then try to execute the code. When they execute the code, they'll end up seeing the error messages that you get, and then it goes directly back into the system and say, hey, look, this is what I saw as the output, how should I end up working with this, right? So it's not like you give it a prompt and it gives you back out code. When you use the agentic systems, it's not just giving you back code, it's actually executing the code, looking at the error messages, re-executing the code, changing it, and then doing this in a loop. And that's completely different than using it just as ChatGPT, like, oh, hey, ChatGPT, give me code, because it's actually able to see the error messages that it gets from the code that comes back. And that's really where the difference comes into play, right? So, in fact, this has been kind of highlighted recently. NVIDIA research has actually mentioned that small language models are likely sufficient for the future of agentic AI, because most of the improvements, most of the accuracy actually comes from the agentic loop that you have around it, not necessarily the accuracy of the LLM itself. Having a more accurate LLM does actually help for generating better code the first time, right? But a lot of the agentic systems are actually not as reliant on the accuracy of the LLM for code generation as you would think they are. And there's a lot of research that's basically saying that most of the accuracy is not coming from the LLM, but most of it is actually coming from this feedback loop of the system, right? And so if you've been scared to adopt some of these systems because you've seen the stuff that ChatGPT can spit out, I agree. It can scare the crap out of me. Some things that it can hallucinate. But the reason why it's working in the context of code is because it does not have to rely on that first output being correct in order for the system to work, right? And so, if you're going to start getting into this LLM coding space, again, I'm going to start talking about the general tools first, and I'm going to talk about a tool that we've been building that kind of destroys them in accuracy. But we need a baseline to understand what we're going to talk about first, right? And the baseline here are basically these three things to start. Right, you have Claude Code, you have Codex CLI, and you have Gemini 3 CLI. If you can try out Claude Code, I would recommend that at this point in time, and it seems to be kind of like a general sentiment, Claude Code seems to be by far and away the most accurate. Now, where these other tools come into play is that Codex CLI is the one that's by OpenAI. So if you already have a ChatGPT subscription, then you can probably already start to use Codex, which is kind of like a nice add-on here. And Gemini, this one, again, if you look at the most recent results, Gemini and Claude are the ones that are definitely on the top. GPT-5 is about 10% less, accurate or some measurement, right? But basically, what it ends up being like is, the Codex one ends up being like basically a first-year undergrad who just started school versus, like Claude, which actually knows how to write a program that works, right? So Claude and Gemini tend to be the ones that actually work a lot better, at least at this given point, than the one that you find in Codex. But if you have a ChatGPT subscription, that's one reason to already use Codex, because you've already paid for this. And with Gemini, I mean, the reason why Google's been able to get into this game is because if you already have, say, a Google Enterprise subscription or something through the university or something, then you might already have a Gemini subscription as well. Whereas Anthropic and Claude seems to be by far and away the best tool for the software engineering right now, but you probably would be paying for this on your own because you're unlikely to have any subscription for it to start. And those subscriptions go from about $20 to $200 a month for pricing. So it could be kind of expensive to use the full Claude Code version, but there is a certain free tier, and I'm going to show you in a second how to get this all going. But just pointing out that there are 3 different ways you can get into agentic AI coding. Definitely Claude Code is the best. Most likely you can get into Gemini 3 pretty easily. I wouldn't recommend Codex, and I have a lot of examples to show that, but that's probably outside of this talk. So before we even get into any of the specialized systems or whatnot, I want to make sure we can get everyone on the same page of what is Claude Code, what does it look like to use it, and how do you get it running? So if you haven't done this yet, right? Now let me switch over to this. So if you haven't gotten Claude Code up and running yet, if you just search for Claude Code, right, it'll come right up in here. Oops. Oh no, this is that's actually Claude itself. Wait. Oh, is it because I'm already signed in that it won't show me like just the? Well, it's not taking me just to the. Okay, I guess it's because I'm already signed in. That let me just do this in an incognito window then. So if you type in Claude Code. Wait, why is it not showing me the window that I was? Claude.com/product/cloud-code. Okay, this was coming up at the top of my on the top of my Google before. I'm not sure why it suddenly changed it when I went out on stage here. But so basically, if you type in Claude Code, it's most likely going to bring you right to this page, right? All you have to do is if you're on a Mac system or a Linux system, you copy this in, you throw this into the terminal, and this will get you Claude Code set up, right? Now, what is this beast that you will have just installed? Well, I recommend that when you're first starting to use this, if you're used to doing a lot of programming yourself, what you might want to do as well is you might want to go to your VS Code, you go to extensions, and you type in Claude. What you'll see right here is you'll see that this extension, hit install, and this will put Claude code right inside of your REPL, right? So this now gives me a window right here. I guess it's a little bit weirdly sized. This is now Claude Code running inside of my VS Code, right? So what are the types of things that you can do with Claude Code? Well, as I said, you can. This is a tool for agentic coding, right? So here, let me do something like generate the code for the Lock-Volterra equations in Julia, and write a script that solves them and gives me the plot in phase space, right? So you can do something like this where you'd say, okay, this is something where, again, people here will have said, oh, a normal undergraduate student should be able to run, should know what the Lock-Volterra equations are and be able to solve the equations. Well, then it's well within the space of Claude Code to be able to churn this through. And if I have a script open here, you can see that this is actually tied to my script. So testscript.jl is open on this side. And so it knows that what it's going to do is going to use the prompts here to write into the script over here. And we'll see in a second that it will come up with something. We'll say it's allowed to write here, yes. So I had to give it permission in order to write to a file, but you can see here, using differential equations, using plots. Here's the Lock-Volterra equations. It's almost exactly how I wrote it inside of my notebooks. It's almost like it used my notebooks as training data online. Came up with parameters, right? And so, boom, then you can see that this is viable code right here, right? So this is the basis of Claude Code. If you haven't been using a system like this to help you write code, you should instantly look at this and say, oh, again, I showed you all the installation steps. It takes you about 5 minutes, and you're already right here, right? Now, you can start to do something like say, okay, look at the frequency of the oscillations. I know that frequency is spelled wrong, but it doesn't matter. Look at the frequency of the oscillations in the rabbit population. Choose different parameters. Choose different parameters so that it's very fast, right? So you can start to do things like this, where again, what it's able to do in this context is because it's actually, in this context, it's able to edit your scripts, it's able to run the code, right? So what it's going to do is going to edit the script, it's going to be able to do things like run the code, and then it'll be able to do this to be able to iterate on. Well, this time it didn't actually run the code, so I'll just say run the code, look at the plot, and given the plot, double check if your assumptions are correct, right? And so what you can see with this kind of agentic system is that it's not really just the prompting system itself, but it's the prompting system mixed with the tool to be able to run code, right? So first what it did here is said, okay, I'm trying to run this, and I see that differential equations isn't installed. I get an error message when I try to run Julia. I don't have differential equations installed. So what it's then going to do is it's then going to run this, add differential equations. So it's installing the package for me. It's starting to do this system, right? You can start to see the loop in action. So I'll let it run this loop a little bit, and then I'll be able to, while I do the next part here, right? But this is basically one of these agentic systems, right? It's a system that is not just for LLM prompting, but it's a system that is also including the code execution and the reading the results and everything as well. So the first things first, this is what I kind of call step 1 and 2, right? So you set up a system like Claude Code. Again, you could use Gemini CLI or something very similarly, but you set up one of these systems, and the first thing that you want to do is start to do local orchestration inside of VS Code, right? What begins to happen with these systems, though, is that you can start to see that they're actually rather capable at, this one is going to cook for a while to install that. Let me actually cook it for. I'll just say just use ordinary, or let me add ordinary diffq first, right? So you can already see in here right now that it's like, oh, it tried to do the whole differential equation solver. That's going to take some time. I know that I can make this go faster by making it only use just one part of the ODE solvers. So I'm going to just step in. I'm going to hit escape. I'm going to cut it. I'm going to add the packages for it, and then I'm going to tell it just used ordinary diffq directly rather than differential equations in order to make this run and load faster, right? So I'll do this in a way where I'm going to set up the libraries for it. I'm going to set up its environment, and then I'm going to then put this back in here. It's going to accept, and it's going to accelerate it, right? So this you can already see that there's a given amount of expert knowledge that is required to be able to use these systems correctly, right? It's going to then switch over to this library, and it goes, oh, with this library, it can run this a bit faster. I'm going to try to run this, et cetera, et cetera. Oh, but it was doing it in a global environment, so okay, maybe it needs to do it in a different environment, yada, yada, right? But now, there's a few things that you start to see with this, right? So again, as this is running, we'll see that it'll be able to kind of improve itself and everything. But there's two things here. One is that you can see I have to give it a lot of permissions, and the other thing is, two, I might want to be doing a lot of these projects at the same time. So again, we'll watch this go all the way through, but while we do this, we need to ruminate. Can we now come up with strategies where we then begin to scale this, where we start to have, say tens of agents all running at the same time, which are doing different parts of our projects and trying to improve different parts of our code, right? Now, one of the issues that you'll see with a lot of these agents is that they can only store so much information inside of their memory, right? And so if they can only have so much information inside their memory, how can we start to orchestrate this where it works out well? Well, the first thing that we need to consider is let's make it so that we break up the projects that such a system is going to work on into very small chunks. And it turns out that we do have a system for doing this already, right? We have systems like GitHub, right? So if you think about what we do with GitHub, right, we basically, so if I go to GitHub SciML /ordinary diffq, right, What we do with the system like GitHub is we say, here is a ledger of the current code, and what we do is we make pull requests, which are small changes to this code, and then so that way you don't have to understand everything that's going on. You just have to know what's going on with your piece and make small changes, right? This is how a lot of our systems are already working. So if you want to then start to scale up the way that you use these systems, rather than just working on one little part of the project that you're looking at right now, what you want to start to do is you want to start to say, okay, let's make it so that way I have a Git repository that is the source of truth, and let me now have all the agents be pulling from the current Git repository, making pull requests, making small changes at a time, right? And so if you do this, then you don't necessarily need to look at any of the code locally, because again, it will run the code and be able to double check things. Your CI systems will be able to double check the code. At this point, you don't need to even run it at all in VS Code. You just need some way to be able to prompt it and tell it to start working on online, right? So this is where you can start to get to Claude Code CLI, right? So if you do this, you can say, for example, type in Claude here. Actually, let me do this to a sandbox. It's going to be a little bit safer. So I'm going to make dir sandbox, cd sandbox. So this is going to be like not like a true sandbox, but I can make dir test cd test, and I can open up Claude here. And what you see is that you get a whole agentic system here set up, which is a version of Claude that runs in your CLI, and you can then say make the script for the for solving the Volterra equations. Or actually, let me come up with something that's a little bit more, just so that way you can see the power right away of this kind of system, right? So let's say I'm looking at this library right here, ordinary diffie-q. It has a very small, README. The README doesn't have very many examples. So let me do something like say, in this repository, make a pull request that adds an example for solving the Hodgkin-Huxley equations. Is that a good one? Or yeah, and just give it the pull request, give it the PR, give it right here, right? And this will churn through. Now, there's a few issues that you want to do in order to make this work out, and you'll see it in a second, right? The first thing that you have to go is, well, if I was to give this if I was to give this full access to everything that I have on GitHub, that would be pretty scary, right? Because if you're also giving it access to be able to write things, you're giving it access to be able to delete things, right? And then, so how can you start to do this where this is both effective and able to do a lot of work and safe at the same time, right? So here's a system that I put together that I believe that a lot of people, when you go beyond this piece of running it one piece of code at a time, here's a system that you should be considering as well, right? So if you have some kind of HPC node that you can access often, you can set up this node so that we have a bunch of you can set this up so that we have a bunch of tmux sessions, right? So is everyone here familiar with tmux? All right, not so many people are familiar with tmux. So if I go here, and so I go back to here, if I SSH over to the system, right? If I SSH over into the system, right, I can, well, I don't have this set up as passwordless SSH on my demo account computer. So I do have to sign in with my phone to verify it. But once I give it access, I'm over in the system. Now, the issue with working on a remote computer in an SSH is you don't have a persistent terminal, right? But if you use tmux, right, if you use tmux, this gives you a persistent terminal. I can actually then go over and I can SSH again. I can SSH again, just need to right? And if I do tmux ls, you'll be able to see all the windows that I currently have open. So for example, I can get into this window, which is the tmux session. Well, this would be the most recent one. So it'd be the one that was created on January 7th right here. So if I tmux attach -t, this should be session 20, right? If I say hi over here, it should also be saying hi over here because these are exactly the same session. What this means is that I can actually close out of all of these. I can close out of all these windows. I can go back in here. I can SSH back into it. And I'll have to verify it on my phone again. I can SSH back into this, and I can tmux ls, tmux to ls. This window is still there. Even though I closed all the windows for it, I made it so that way it's always running on a remote machine. So even if I turn off my laptop, it is still running. So I can then tmux attach dash T20, and I can get right back into that same session. In fact, that session is so persistent that I can do this right here, where I can go on my phone. I can open up a terminal right here, and then I can sign in. Once I sign in, I can tmux attach dash T20. I can sign, oops, I typo. Tmux attach T-20. And now from my phone, I can say, Claude. So I'm going to run the command. So now I'm going to show you something. So when I'm running this locally, right? If I'm running this locally, you saw I had to keep on giving it permissions, right? And so if you want to start making it so that way your AI agents start to have full reign over what you want, you can start to do things like. I'm just going to show you, right? You can be literally sitting at karaoke, and you can do things like dash dangerously, dash dangerously. And now, if you do this, we need to start talking about things like what's the word? Sandboxing and everything, right? So this is then a sandbox system. Again, this is a system that is now running at MIT that allows for all these persistent sessions. So it's not tied to my laptop. It's not tied to my phone. If I close any of these windows, I can always reopen them back again. But now here I've given it a session where now Claude has set up to be able to do any code changes that it wants on the system, and it won't have to ask me for permissions anymore. And then I'm just going to tell it, for example, take this. And add to the README I don't know, what's a nice set of small equations that people like? Harmonic oscillator equations. Right. So boom. Now this is something where I can close my computer, I can turn it off, but I still have agents running, making pull requests for me, right? But then the first question they have to be asking is, how can you make this safe, right? One of the ways that I then recommend to make this safe is, so here, let me grab a session here, right? In order for it to be able to have any permissions to be able to push into your libraries, you need to give it explicitly permissions, right? So if you have this set up in a different environment. So here, for example, locally on my own machine, I have GitHub set up, right? Because I'm going to be merging code on my own, and I'm going to be working. But what I can do is on this remote machine. Hold on, I'm not getting the. On my remote machine, I can actually give it a different set of permissions, and let me show you how to do this. Is there rate limiting that's going on with the Wi-Fi here? Because it's not hopefully it's not rate limiting all the yeah. So okay. So then so it actually should already have this PR ready. So I'll show you this in a second then. Yeah, so it's going to say the GH auth credential is not set up, right? Because on this remote machine, I'm going to have it sandbox, right? So what is the solution to make this so that way this can be safe? What I found to be the most effective solution is to make yourself a bot account. So you can see here that I have a separate account for GitHub that is only set up. So this is Chris Rukaka's Beep Boop edition. So it is not set up to actually be able to merge any pull requests or anything. It's not allowed to push to master. It's only allowed to read and write in such a way where it can create pull requests. And so I can make this machine be dangerously unsafe, but it still is not allowed to make the final say on any code. I still have to make final say on any code, but you'll see that it's able to make all sorts of pull requests using this system, right? So what I can do then is I can, with GitHub, you can make alternative accounts that you then can switch between two on a single machine. You can set the bot auth to only this account, right? So how do you do this? So let me cut out of here so that way I can just demonstrate this. It's not sending me the auth anymore. Oh, good. I already have another sandbox. So I would do GHAuth, GHAuth login, right? If you GHAuth login, now if you GHAuth login on your remote server, the server that you're SSHing into, this will only give that server the permissions here, which it can be separate from your local permissions. And so what I'm going to do is I'm going to ask it for this token, and then you actually if you don't have a text-based browser, what you have to do is you have to take this, you sign in Claude through here, and you take this token here. And then boom, this account, that everything that I'm SSH'd into in that other machine, right? Again, this is in Cambridge, right? So again, the system that is currently running in Cambridge, so at MIT, now has the authorizations to only act as me through this Claude account, which has the permissions to create pull requests, but doesn't have the permissions to be able to do anything, to actually be able to merge anything, right? Let me just finish the auth here. So congratulations, we're all set. And so now what this means is that on this remote machine, even in this other tmux window, I can tell it to, I just did the GHAuth, used GH to make the PR. Well, I guess it actually just made the PR because it just realized I just re-authed. And then, so then I can say, wait 30 minutes for CI to run, and then double check the results. Results, iterate, and try again. Right? And so you can start to create these bot armies where, again, this one I won't have to look for half an hour. And so while this is running for half an hour, I can move on to the next thing I'm working on. You can start spawning on all sorts of these bots. And what does this actually look like? I can open up this pull request over an ordinary different queue. You can see that it added a harmonic oscillator example to the README. It has the summaries here. And you can see that if it did it right, it should be adding to the README. Here's the LaTeX for the harmonic oscillator. Here's the equations, and here it is right here. This is actually the first second order ODE example, so it looks pretty good. I just double checked it, and boom, let's be reckless here. Now, you can see my bot account does not have the permissions to be able to merge this, right? I can jump over to my other account though, and I can jump over to my other account, and I can hit merge right here. There we go. Since it's only to the README, I feel like this is like the right level of reckless, right? But there you go, right? So you can start to see how you can start to increase your speed, right? I just added to the README something that only took like, a minute or so. And again, it's a completely safe form of doing this because I set this up as sandboxes other accounts, and I can immediately spin up new sandboxes just by doing this command where I just keep on going here, and then I keep on spinning off some more sandboxes, and over and over and over, I can have tons and tons of these bot accounts running, right? And so you can actually see the activity of this bot if you're curious about how active it ends up being. In the last few days here, it made 2,000 contributions since August, and I think in the last month it made 273 pull requests, right? So we're talking about something where it's just like a fairly large active environment that is just running by just saying, hey, I'm not going to try to deal with this locally. I'm now just going to give it full permissions to be running on a sandbox, right? Now we actually took this to a next level. So if you go to the sciml.ai, I'm going to show you the latest blog post we put out here. What we did was we started to have a bunch of health bots where we'd say, there's a lot of routine things that you want to do to the code, right? So again, now none of these bots are going to be able to say, do your entire project for you, right? If you try to just sell it like, come up with the novel equations for, my climate model and write the paper, it will fail gloriously, right? So what is the right way to start using these kind of bots that exist, given that that they only have like the capability of, say, a sophomore undergrad that you've taught on one given topic for, a few months, right? What we've been starting to use them for is to say, okay, we have hundreds of packages that we're trying to do this stuff on, but there's a lot of routine changes that we want to do. So we've ended up creating sub-bots and for a bunch of these different things. They can do things like check the CI health, be able to try to solve an issue. Normally, if it tries to solve an issue, it'll fail, but there's a lot of other things it can do as well. So for example, it can look at parts of your code and try to do a static improvement. It can do things like a performance check. It can do interface checks. So let me actually just pull some of these up in ordinary Diffie-Q so you can see some of the pull request and get some ideas for how you can be using this yourself, right? So here, for example, you can see Here's one that came up recently. What it did was it basically just said, oh, I saw that there's a compat helper request that came up. I'm going to then test locally on my machine. So it spends a few hours checking whether the latest version of a new package that came out is correct. And it actually saw that it needed to do some changes. And so it made the changes to multiple project.tomls in order to make it so that way this version was able to be merged, right? So that's one thing. Version handling is something that's very easy for bots to do. In fact, if you have it set up so that way you tell it where to find information about where breaking changes occurred, dealing with breaking changes is effectively trivialized with this kind of work, right? In order to improve this a bit, actually, let me show you one little detail here. Hold on, let me see if I'm able to auth again. I'm being rate limited by MIT. All right, but okay, if I go here. So one of the ways that you then begin to improve this as well, though, right? So if you go down to CD, you can cd.claude, right? You can then go into vim claude.md. Vim claude.md, right? It turns out that this claude.md file is a context that it gives with every single new agent. And so you can start to tell it all your preferences in here, right? You can start to see some of the preferences that were used to make it so that way this system is more automated. The first thing, some of the things I tell it to do is, you should never force push over the branches, shouldn't force push over main. Again, it doesn't even have the ability to do this on the global repository. So most of the time it's safe, but you just try to make it so that way it never tries to do these things. But some of the things that's very useful to tell it as well is to tell it, when you want to check for CI results, wait for about an hour before checking CI results, so that way it waits for the CI to be completed. This makes it so that way it will make a pull request, it will then wait on its own for an hour, it will check the CI results, and then it will make a code change, and it'll do this autonomously. So some of these bots can run for about 6 to 8 hours, just doing one change, checking whether the change did something, a small change, checking whether the change did something, and it'll just continually run this. And again, as a TMUX session, I can then go into this TMUX session and see, oh, is this one still running? What is its current state? And you can modify and you can kick it back in the right direction, right? But you can start, if you build out this Claude code, I'm going to share my Claude.md if people are interested in how this is all set up. But once you start to set this up, effectively they begin to run autonomously and use GH to make all of its pull requests. And this is how it knows, oh, I should always use Julia code, I should always use GH, I should wait this long for CI. All this information is embedded with the Claude.md file. Yeah, and so let me then show a few more, another example of this in practice then, right? So here's another one that it was able to do, right? So for example, the static analysis version of the bot, so I'll show you the bots in a second. It spun up a static analysis version of the bot, which said it's going to look at these sub packages, and it started running jet tests on each of them. And I believe in these ones, it found that there was some, most of the jet tests passed right away, and so these ones it didn't make a code change. But in other pull requests, it would actually go and say, hey, look, I found some allocations, or I found some trivial type instabilities, and it'll fix the type instability and add the test for this. And so we now have a bunch of these bots that are then spawning on all the different repos and doing things like static analysis checking, doing things like improving performance, improving allocations, and all these things autonomously, right? So then the question is, how do you start to make this autonomous? A lot of this is set up in internal scripts, which I'm not entirely going to share because they have keys embedded with them in them, right? But this is what I then have as this. Well, what you can do is you can start to say, okay, I have, I can then set this all up here where I'm going to go here, and then I'm going to, I plan to, by the end of this week, actually sanitize the runner that I have here, so that way it's keyless to be able to run this. Basically, what we should be able to do is I should be able to just say, run, re-enable the SciML agents, let them run any tasks. And now because I have this authenticated with GitHub, right, it's set up for the Claude account, and I have this set up with Claude on here, it should be able to run SciML tasks enable, and it'll enable all 13 of the bots here. And I should be able to check this inside of my dashboard, and in a second here, you should actually see it kick off about 20 to 40 agents, which will then start making a bunch of pull requests. And so again, as I'm doing the rest of this talk, hopefully about 30 pull requests or so should be made. And yeah, you can see here that it just did a few direct ones. So in parallel particle swarms, it just kicked off something to try to directly solve an issue. In SIMO benchmarks output, it's improving the static analysis. It's doing a CI check now of modeling toolkit neural networks. It basically just took over a whole CI node, a whole HPC node of 128 cores, and now it just spawned a bunch of these jobs according to all the different types in the blog post, right? And in a second here, we'll look at all the pull requests that it's opening up. And so you can see that this is then a very different way to be coding, right? I'm no longer looking at my code saying, oh, is my code fast enough, right? There's just a bunch of agents checking all the different portions of the code. They will find a test snippet and say, okay, I want to see whether this code is as fast as possible. I found allocations in it. Here's the pull request that adds that fixes your allocations and adds a test for it. And you just have hundreds of these just continuously running at the same time. So again, you can start with this just by using VS Code locally, and you can just be using Claude Code directly in your VS Code. But I encourage you to start using the CLI versions and start to build out these systems that is in orchestrating tens of these and hundreds of these running at a time, because you can see that once it starts to scale up, it's able to do quite a bit. So that's just Claude Code on its own. Does anyone have any questions about using Claude Code and orchestrating in such a way like that? Yeah. Oh, yeah.
I don't know if I was first.
Everyone's
okay. Well, this was an amazing presentation. Thank you, Chris. Well, I want to know how did you build the script to have the CLI tool to control all of the bots in parallel? Did you use Claude to make it?
Yeah.
How did you make it with the shell script or something?
Yeah. So I mean, it started with something like I started writing the first part, but then Claude ended up helping out with the other part. What ends up happening inside of this as well. So let me go into a little bit of the internal agents and internal scripts in parts where I know that it doesn't have keys, right? So I have a few of the scripts that you saw, right? So well, first of all, I have some things like Claude Skip that it knows that does the dangerously skip permissions. Again, there's a version of this for Codex. There's a version of this for Gemini. So -- YOLO is a thing for Gemini. So it basically knows, these are the special commands that you should be running. Inside of the SIMO agent monitor, then I started this off, and then what ended up happening was, I ended up building like agent version 1 for CI health check and for a second thing, and then I just said okay, now create a version of the agent for dependency update, create a version of the agent for minimum version. And once it already saw a lot of the different aspects of these scripts, it was able to generalize it quite well. But then the main thing that ended up going on here as well is that it also has a checker that happens every week. So at the end of every week, it looks at all the pull requests that it opened and looks at all the comments that specifically I gave to the bot, and it will then do a pull request to the internal scripts that updates the scripts based off of the things that I've been asking for. So it's been running this for a few months now. This is where it came up with the bot for the It came up with the bot for the performance improvements itself, just because of the number of times like you tell people and like, I can't accept this PR because of performance improvement. It realized that, hey, what I'll do is I'll check a test and I'll just check the performance, and if it has allocations, I'll try to solve those, right? So that all just came from it just iterating on its own previous results from that. So it kind of started with me in there, and I'm actively involved in watching what the bots are doing pretty much every hour, either from my phone or on the computer. But I'm pushing it in the right direction so that way it doesn't go off the rails, but it's also autonomously helping and fixing itself. So it's a bit of both, yeah. But that's also why I want to make sure that before I show all the scripts, because I know that it has some SSH keys and such in there, so that's why hasn't been made public.
Yeah, I also have a question. So, what's your thought about the cost of this compared to the value? I know right now the prices of tokens is quite cheap, but there's also some cost associated, and also if the tokens are priced more according to the energy consumption, and also about the cost in terms of electricity and to the environment. I mean, how do you see the trade-off between the value and the cost? Yeah,
that's a good question, right? Because I mean, yes, by kicking off 20 agents right here, what I did just during this talk, right? probably is using the electricity of at least, like 200 normal people, right? So there's an environmental cost that you should be considering with this. It does give you a lot of productivity. Now, I talk about this a lot in some blog posts. I'd say check out the recent blog posts on a stochastic lifestyle. You might have read these on Hacker News and stuff. This one went around quite a bit. But these two blog posts, Cloud Code Sucks, but it's still useful, and a guide to Gen AI for expert programmers, right? One of the things that I talk about with these systems is that they can get really stuck really fast. So think about it as, if you're mentoring some students, one of the things that you'll see is that, there are projects which the students can do, and sometimes the student is just incapable of doing the project. If the student is incapable of doing the project, sometimes trying to train them on that project just doesn't work. You just put them to a different project, right? And the same thing will happen with these agents, right? They'll open up some pull requests. In fact, the one I can think of one from yesterday. It was on Rancho's library. Which one? Beachtrees.jl. No, let me look in SIMO. So what you'll find is there'll be all these different cases that come up of rooted trees, such that's the name of it. So for example, it was able to be pretty effective in some cases. So for example, when I was adding static analysis tests, it was able to find out, okay, I could figure out, here's how I add jet to these different tests, yada, yada, and it was able to do this quite well. But we really just kind of work on this space of, if it starts to go into a loop and starts to do things wrong, you don't even try, right? So here it created a pull request that tried to add 3 new features. It did not get these features perfectly correct. It got them about 90% correct, but it wasn't able to respond to the comments fairly well. So you can see over the span of 2 days, it was trying a bunch of different things in the code. So it probably used, a decent amount of power to be able to run this. But at the end of the day, we saw, hey, it wasn't able to do this. And it started disabling tests. This is actually a behavior that you'll start to notice. If it starts to do this thing where it's like, okay, run back and forth, and it's not able to figure something out, the moment it starts to disable the tests, just click close on the pull request. Don't even try to use it anymore. So you might think about that as that was wasted work, but in terms of human time, that was no more than a minute or two. So in terms of human time, it was no more than a minute or two. I let it just keep on running. I saw it started deleting tests. That's the moment I just say, I'm not even going to look at what it wrote. And so in terms of human time, it's very quick to make this very productive. But the downside is you are using a ton of power. I mean, again, there's an entire HPC node that's only running this bot, and it spent 2 days on, so 2 of its 128 cores was just on complete junk that we threw out. So there is an environmental cost to this, but you can see that there was 175 pull requests that did merge, right? And so there's about 175 that didn't merge, right? So we have about 50% of them just complete junk energy, but the other half works out pretty well. And if you make it so that way, you just say, have some keys, or you just say, when this is junk, I'm not even going to waste my time with it, then you can be rather productive, even if it is somewhat unproductive energy-wise. Now, is that good for the environment? I think that there's a lot of discussions to be had here, which are, the environmental and social impacts of this are a different discussion than the technical, how do you do this and how do you make it productive? And I think that we do need to talk about the environmental and social things there. But at least with the prices that they're at right now, they're being subsidized heavily by VCs. Use this and make your repos really good right now, and we'll figure out the other stuff later.
For the pull requests that get stuck or that don't really work out, and I'm hesitating to copy your setup that directly makes pull requests. I feel like I would want to review it first before putting it out and notifying all the other contributors. Do you have any ideas for such a setup?
You could make it so that way it makes pull requests to your own fork of the library, and then you pull requests from that. That's one way to make it so that way it's a little bit safer. Because SciML in general, I have BDFL of SciML. I'm happy just to throw this out there. But yes, when I do things outside of SciML, I don't make it just put a pull request out. And I do a pull request to my own fork, and then I manually open up the pull request from there after I double check the code. But you can see here, this is a pull request that was just opened 3 minutes ago. It's fixing package compatibility by removing test.project.toml. So it found that actually this library had a test project.toml, even though we normally run things without the test project.toml. This is probably one that we can merge right away. We'll wait for the CI test to run. It'll iterate on on its own, I can check the agent, but it was probably going to wait the half an hour here, going to wait for the test to run and iterate. And so this is probably something that's quick to merge, right? But then there's some that, yeah, we'll delete right away. And yeah, if it's not a repo that you own, in terms of everyone here in the community, don't set your bots on other people's repos because it will create a lot of junk. Again, 50% of it's junk, but it's okay in your own repo to just be junking half of them, right?
And one more question, like I'm using Claude, the agent, but via Copilot because that's what I have a subscription for. Do you have any experience with that, like Copilot CLI?
Yeah, so the Copilot CLI, the thing with the Copilot CLI, though, is that you generally don't get the latest Claude agent without having also the Claude subscription. The difference between Claude Opus 4.5 and the Claude Opus 3 or whatnot is gigantic. So I definitely would say cutting out cutting out the extra subscription, going straight to Claude and getting the actual better model does a bit better. And again, it's fine to do a lot of this locally, but if you're going to scale this to running a lot of agents, you want to pull this away from local and you want to get a persistent session, because a lot of these sessions, again, when I'm saying like, oh, this thing needs to run for 8 hours, if you have it running on your computer, that means you can't turn off your computer for 8 hours, right? So if you set it up so that way you have a persistent session on a remote machine and you tmux to it, then you can, from your phone or from your computer, you log in, you check it, you give it a nudge, and then you do this. And once you start getting to that level, I think that you probably don't want the GitHub Copilot one. I would just drop all those, just because it's easier just to orchestrate it through the CLI agents. But maybe that's just a personal thing. But I mean, I showed you my setup here. Within 5 minutes, you can get something similar to set up to this. So again, so I'd recommend doing this if you have like a remote machine that you can SSH into that has sufficient power. This is a really decent system. The other thing that's nice about this is that it also sandboxes it, right? Because if you give it dangerously skip permissions, it could delete everything on your machine. The worst that happens is it deletes everything on that machine in C-Cell, and we just have to wipe the machine and start over again. We only have to wipe it every few months or so it's okay. If I had to wipe my laptop, that would be a very different story, though. Yeah.
Thanks, Chris. Nice presentation. Given that you used Claude and enabled dangerously, could you maybe explain to the rest, maybe in a few minutes, what prompt injection is and how it can steal your credit card information? For responsibility's sake, right?
Yeah, I mean, so I mean, with the prompt injection, I mean, like, when you do dangerously skip permissions, it has access to everything on that computer, right? And it will run, and it'll be able to run code on your computer. It could do things like delete your operating system because you're giving it full access. And when you say dangerously skip permissions, it doesn't have to ask for permissions to do anything, right? I think that the way to then do this effectively is you just have to sandbox it, right? So you have to be running that Claude agent inside of a sandbox where all of the information that it has access to is only stuff that you want it to be able to run with, right? So, for example, on the agent on the machine that it's SSH'd into that I run the agent, it does not have access to any of my personal information. Like, it's just like it's a Linux box that has only Claude installed, only Julia installed, and the only GitHub authentication that it has is to the Claude agent bot, right? And so, yeah, it will make some weird pull requests every once in a while, right? But it doesn't have enough information to be able to throw everything like that. But this is also why I'm saying if you're going to use the dangerously skip permissions and stuff, either be running this inside a Docker container or do this non-locally, because you don't want to do any of that locally. Because yes, otherwise it would have in your computer all of your credit card information, and it could make a pull request that puts all that in there, right? So again, I think that the main answer to a lot of this is sandbox appropriately, and the easiest sandbox is just to have a completely different machine that has permissions and access to nothing. Yep.
So I like Mistral AI, and they have Mistral code. I'm wondering why it was not in the list of your comparison. Was it just lack of time, or is there something there that would be missing?
Lack of time. I mean, well, Mistral is mostly an orchestrator over other models, right? I was just basically pointing people to the three main models that, Mistral, I believe, uses a lot of the Anthropic models by default, right? Yeah, so I found it more effective to just go straight to the Anthropic models. I mean, because I don't think it's so difficult to build your own orchestration on them. But people are like in Mistral and things like Cursor, and things like this. So if you're more comfortable, if you're familiar with those, it's totally fine. I kind of just tell people, like, I think sooner or later, if you want to be doing more than just working locally, right? Using the CLI, just doing it all through SSH and command line is it gets you up to scale really quickly, and I would just cut everything else out. But again, that's maybe a personal thing. But I showed you the setup here, so it's difficult for me to see how someone else can get you more customizable thing in like the 5 minutes it takes to set this up. So, but to each their own.
Thanks.
So I do want to, we'll take the last question here, and then I want to get to the last part of the talk here.
Hey, Chris, I'm wondering, for you and for a lot of people, you have a lot of experience. You know how to discern what is correct and what is not correct, and even though you're gating the changes with pull requests, I'm wondering what are your thoughts on people who are just starting out with coding and being confronted with these agentic tools right away. I'm concerned that people that have no experience and start using this will never get to reach the experience that you have and a lot of the other senior people have, and that way they will not be able to discern what is correct and what is not correct, and we will reach a point where all new people that start coding in the next generation of programmers will never be mature enough because they offload all their thinking and all their responsibility to these models.
Yeah, it is a good question. It is a good question. I mean, because when you start to see this workflow, right? The thing that I would kind of start to say is this workflow is not necessarily new, right? This idea of here's a workflow where I just showed up and here's a pull request where it changed to formatting to runic. Here's a pull request where it changed package compatibility. And in fact, if I had my email open, you would have seen that it just created like 30 pull requests. And what I would do is I just go through pull request after pull request, looking at the code change, saying change this and whatnot, right? And while that might look to many people like a new workflow, it isn't a new workflow, right? Because there are a lot of people who have been doing that workflow for many decades. That's your professor, and that is the senior dev of software company, right? And so normally, if your professor is not writing their own code all the time, I mean, people in here tend to be writing code, right? But a lot of professors, right? You have a lab of 16 people, and your students come in every morning. You look at their code, and as the expert, what you do is you don't necessarily write on their code. You look at their code and you just say, that's wrong, that's wrong, that's wrong, come back tomorrow and fix it, right? That's exactly the same workflow as this. Now with it, for me to be able to say, instead of paying for 16 grad students, I now have 16 grad students, but I also have 48 of these agents that will respond to me at midnight, right? And so it isn't a new workflow. It's just saying we're now giving the ability for everybody to have their own grad students, right? And then the question really comes into play is this a good thing for learning, right? So if you already learned how to do all this, I think you naturally progress into this type of field where you say, okay, I've written so many differential equations that when a PhD student comes to me and they say, hey, look, I have this ODE and it's running slow, I know the first 20 things to look at, and I just look at their code. It only takes me like 5 seconds, and I'll be like, okay, you wrote it out of place instead of in place, and you should do that. I've seen this thing so many times that this is why code review is so easy, right? And so this kind of workflow is set up where it's just say, if you've gotten to the point where you're good at doing code review and you can do it quick, swiftly, and accurately, and safely, the main thing is safely, right? Because you have to be able to know, when am I doing code review in a way that is fast, but if I made a mistake, I'm okay. I'm like, okay, I'm looking for this kind of test and everything, and that comes from a lot of experience doing this, right? If you've gotten to the point where you're very good with code review, this is an accelerator to that. Now, if you're someone who's still writing code themselves, should you make the jump to be doing only this code review style? I think that there's a major question there in pedagogy that's coming up. I do think that to a certain extent, you need to write a lot of code yourself in order to get the feel for how code works. But I also think that this style, I don't think that just writing code actually teaches you how to work through code review. I think that a lot of people, when you first become a professor or senior dev, you instantly hit this, right? Because you work, in the first, for your 5 years of your PhD, the first 4 years of your postdoc and whatnot, you spend the first decade of your scientific life only working by yourself. And then a lot of people have a really bad time transitioning to this, oh, now I tell a student what to do. How do I work through prompting a student in order to make this work? How do I work through code review? Is actually a completely different skill. In fact, a lot of scientists never really adopt it and tend to be individual contributors rather than ones that run organizations, right? And so I kind of think that with the way that things are evolving here is that, again, these agents are not the smartest thing in the world. And so I think that there still will be the path for people who are very good independent contributors that'll be able to beat it on doing things like writing really fast code, or writing code that is very specific, writing code that is able to handle, certain floating point aspects directly. In fact, you can see right now that if I could pull up a pull request, it's like, okay, what is the type of pull request that I would still work on that the agent wouldn't work on, right? I think that this one right here is exactly the type, fixing t-stop overshoot for event dense time triggers. What's going on in this pull request, right, for example, is you have this property that 0.1 plus 0.1 plus 0.1 minus 0.3 is not equal to 0. So if you're stepping by delta t on a number that is not divisible by 2, then you can end up not hitting the points that you said you would directly. And it turns out that AI agents are not able to handle these kinds of numerical analysis issues very well, right? And so I'd say, if there's still room for people who are experts in numerical analysis to be able to handle these kinds of issues, experts in doing things like code performance, et cetera, et cetera. And so there's still a lot of room for individual contributors. I would say that if you're a student right now, I would very well specialize in writing code for a specific kind of issue while learning to also orchestrate and work through code review. And I do think that this code review style might be something that is brought into undergraduate courses more. I've actually been talking with some folks at MIT even about, okay, the first programming course, should you actually start programming by doing some prompting and showing them, okay, here's what the prompt came up with. Now this is what the code looks like. And this is what the pieces of the code mean. Here's how I should change the code given what I see, right? Bringing prompting into the very first programming course. I wonder if it's going to work or not. I don't know. This at least helps out senior devs a lot. How it's going to do to pedagogy is very, very unclear at this point. Hopefully.
How you reach the senior dev, that's the issue, right?
Yeah, which again, I mean, some of it comes from writing some code yourself. But again, if you just write code only yourself, you will never get to that level of, oh, now I feel comfortable with code review. You kind of have to do code review in order to become comfortable with code review. And so it's a different skill. So do you start with that or do you not is a very good question that I don't think anyone has ever had to answer before. But yeah. I think you do have to learn both at the same time, and so I think that we will completely change the pedagogy for programming. I don't think that these, I don't think you can keep these tools out of the undergrad programming course. They can do your entire homework for the first year. They could do your entire homework for the second year, right? The students will be using this, right? And I think that we just had to redesign all the courses around the idea the students will use this as a shortcut. So how do we make sure that they're still learning something effective? And how do we make it so that way they are more competent in the era for which this is a standard way to do things?
Yeah, you need to make sure that they actually learn
Mm-hmm.
as opposed to just offload their thinking, right?
Yeah. And I'll get to that a bit in the next part here. So this is just the standard tools, right? So if you haven't seen these tools yet and you're like, oh, what do you mean standard tools? These are the standard tools. Everyone here can start to download and start to use this today. In fact, by the end of the day, I encourage you, download Claude Code, start using this, start asking your questions. By the end of JuliaEO, everyone should be using some form of this just to double the number of pull requests you're making each day, right? But now the next thing is how can we actually improve on these things, right? So this is just like the baseline. All right, so this is what I'm saying. This is just your daily, like, okay, it's just checking your code, improving your code, yada, yada. But now as modelers, I've been mentioning over and over that this thing is not smart, right? So how do we make this thing better in the space where we also know that, making a $1 trillion training run, a $10 trillion training run is not actually going to be the true answer, right? It turns out that there's some fundamental things we need to think about for improving the accuracy of agentic AI for engineering and modeling, right? So when we think about how this system works, what we can see that makes this system work out well is that it's really the agentic loop that makes it work, right? It's not the accuracy at which it writes code is helpful, but what really makes this thing work is the fact that after it writes the code, it executes the code, it reads the error messages that I got and tries to fix the code and write some more code, right? It's this loop to it that makes it so that way it works better. So the question that we really had was, can we make it so that way this loop understands more about physics, understands more about computational computational science, and it requires less from the agent to be able to actually get right. This is, if we can make it so that way it can understand more about what makes equations correct, if it could get more error messages from it, then it'll be able to correct itself a lot more. That's like the general hypothesis here, right? And again, it's kind of matching this idea of the NVIDIA research to say, maybe small language models are sufficient. So let's assume that the large language models are not getting any better. In that assumption, how can we get more accuracy out of these systems, right? And this is what we then started to build out as Dyad, right? And the key thing here with Dyad is we started to say, okay, let's build a language that works in a specific way, right? So as a language, it is a statically checkable language where all of the equations in the language have units, and so therefore you can check for things like unit compatibility on any equation, right? Nice thing about that then too is that if you ever write an equation for which the units are incorrect, the compiler at a static check time can give you a statement that says this is a physically impossible type of equation, right? And so it can use that to be able to iterate and say, hey, look, I wrote the equation that I wrote down is incorrect. And so the difference here also is that here what I'm writing is like, dir of x equals y, right? All I'm writing is symbolic equations at the very top level. And what we'll use a symbolic engine to be able to generate what the code is directly from the physics. And so that step of, did I create the right code for the model that I wrote down, is a completely automated, right? If we do it like this, then the actual agent, the LLM, only has to get correct the high-level symbolic representation of the model. The code that is generated, the way that it's executed, the way that it's parallelized, all of that being done through the compiler means that there's a lot less that can go wrong for the system, and it gets better error messages because the only things that it's allowed to write down are things for which can be unit checked and can be checked for real compatibility. And this is what we've been developing as the Dyad modeling language, right? So it's a separate language from Julia, but it's a language only for modeling and simulation that then all that you can do, you can write down symbolic equations, and it will then compile by generating the Julia code for you, and then generating the differential equation code and running that. And so this is what we're calling the Dyad system. Again, I'm running a bit short on time here, so I want to get right to the final piece here, so you can get the wow. But it's a system that is has a graphical user interface, so it's like something like Simulink or Magdalika, if you used these tools before. It both has a graphical user interface and it has a representation as code. So it's a one-to-one representation, and all the code is then related to just the equations of the model. The rest of everything else, like how do you turn these equations into runnable executable types of solvers, is all going through a symbolic system, actually the modeling toolkit equation system. And then one of the nice things as well is that at the very highest level, it doesn't need to guess what a lot of these models are, because it's a system that is able to take components from other models and be able to compose them. So you can say, hey, I have an RLC circuit, or I have a resistor, a capacitor, and I have these other things. Connect all these together and create the code that is related to these systems together. And it's able to then use pre-built differential equations and compose them together. So as a modeling system, Dyad is a modeling language that has model libraries and a system for being able to say, make a connection between a quad rotor and a model of heat. And then when it's able to then build you and give you automatically the differential equations for the composition, right? Now, the thing that's done there is the composition process is all symbolic. It relies nothing on the large language models, and so you can be guaranteed that when you compose things, you're getting the correct equations, right? So then the only thing that needs to be done is tell me what models to do, create new components create new equations, and connect between existing models. And then we also give it a bunch of existing models, things like electrical components, so like resistors, capacitors, valves, pipes, clutches, gears, all these things that you would actually have in realistic scenarios, along with fully realistic models of HVAC systems, including two-phase flows for refrigerants and battery systems, including all the the electrochemistry of lithium-ion batteries, nickel-cadmium batteries, and everything. So that way you can start to do things like say, hey, give me a complete electrical vehicle with a lithium-ion battery and with a drive shaft that matches a Chevy Volt, and then it's able to construct that system for you using all these different pieces, where it's then able to pull from pre-built libraries and components, right? And so, I want to kind of get to the bang here at the very end, which is, so this system ends up being fairly powerful and being able to get pretty correct at building models. We, in fact, are trusting it enough that we run live stream sessions on YouTube and Twitch where we ask the general audience to give us questions for models, like, and people just tell us, build a model of a Chevy Volt, right? And we just do it live using the agent fully. And so I recommend if you're curious about this, come to one of our Friday sessions. They're very fun. But I will show you what this kind of looks like with a quick video that we made of dyad in action. And then I'll show you, and I'll start running the dyad agentic system while we're doing question and answering at the end here. But
friction brake system.
But I think that it's not routing my sound. Maybe should I just do the... All right, we'll do this lo-fi style. What? No.
Model using an agentic workflow with dyad. When the driver presses the brake pedal, the braking system applies a force, causing the brake pads to clamp onto a spinning disc or drum, thus creating friction that resists the wheel's rotation and can bring the vehicle to a stop. This friction creates heat that causes the brake pads and disc to warm up. Engineering a brake system requires meeting both mechanical and thermal requirements for safe vehicle operation. Utilizing a modern workflow to engineer this system requires physical models of the friction brake in the vehicle. Here we will develop system models that are typical of the ones required for model-based systems engineering. But we will do so using an AI agent, basically by posing the problem that we want to solve and ultimately ending up with models that execute and predict the mechanical and thermal dynamics of the system. Agentic workflows are fundamentally altering the way that the human and computer interface works, leading to the potential for massive gains in engineering productivity and efficiency. These agentic workflows are a core part of our dyad product and will be demonstrated in this short video. We start by asking the agent to help us create a model for the friction brake that can capture the relevant physical interactions. The agent then does research and provides a mathematical formulation that meets our specification. This step alone is massively helpful. With just one simple query, we potentially have a model that can be implemented immediately, along with reasonable parameter values that are representative of our application. We can even easily iterate on the model by asking the agent to refine the formulation. As you can see from the responses, the agent plans and then returns with a new formulation, including nicely summarizing the changes requested. These changes can be as complex as asking for different mathematical formulations for the physics, or as simple as changing the interface for the model. Once we are happy with the formulation, we ask the agent to implement the model for us in dyad. The agent knows which component primitives are available and utilizes them to implement the model. Now we have executable, fully parameterized code that represents the physics. Note that the code is well documented and very nicely formatted. We also ask the agent to create a unit test that exercises the model under specified boundary conditions. We can test that the component is behaving correctly and also subsequently use these tests to help refine the formulation and model parameterization. This agent is not just capable of generating the model code, but is also contextually aware of the models we are creating, the relevant physics and expected responses, and also key numerical considerations. We now have one part of the model that takes a brake command and generates the resulting friction torque and heat based on the vehicle boundary conditions. Because we are also planning to work with the model moving forward in a graphical interface, we can add an icon to the model. This icon will also appear later in the video when we use this brake component in the full system model. We can go through the exact same process to develop the thermal model for the brake. This part of the model will provide the thermal dynamics of the brake system. We start by asking the agent to help us create a thermal model for the brake system that captures the relevant thermal interactions. Again, we go through several iterations on the model formulation, model interface, and model parameterization. Note that the agent is also reasoning regarding our proposed formulation changes. It even provides us information back regarding how these changes will impact the thermal dynamics in different temperature regimes, so that we can evaluate whether these changes are appropriate for our modeling needs. After we ask the agent to implement the final model formulation, we again ask for a test case to help validate the model. Note the really interesting interaction with the agent. The agent knows how much heat is put into the system in the test, and notes that the heat in the model does not balance, a sign that there is potentially an issue with the energy balance in the model. The agent then performs an energy analysis by looking at the individual terms in the equations. The agent rightly concludes that the system has not run to steady state, and thus should be run longer and proceeds to do so. This is completely unprompted, high-level thinking by the agent, providing insights that can help even experienced engineers rapidly develop and validate models. Now that we have a model created by the agent to our specifications, we also want to visually see the components and how they are connected. There are no graphical annotations associated with this model as generated by the agent, but we can ask the tool to render the diagram and automatically lay out the components. This graphical information is now part of the model, thus ensuring that the model can easily be used and modified in graphical form moving forward. We now have a second part of the model with a compatible interface to the brake that captures the essential thermal dynamics of the brake system. Again, this component is flexible and fully parameterized for ongoing usage. The last part of the model is a representation of the vehicle. Again, we start by asking for a simple vehicle model that will match the interfaces from our brake and brake thermal models. Because there are so many different ways to model vehicles, we provide some additional details on the sort of model that would work for our current needs. We can then change the parameterization and create a test case. There is a really nice interaction with the agent here. We provide a very high-level engineering query to set up a particular kind of test that is used to calibrate the representation of the vehicle load in our model. Note that we don't provide any additional details other than run a particular test and propose values that represent a typical vehicle based on the results. The agent then researches the test, figures out how to implement it in Dyad, and then runs the test trying different parameter values until it finds values that match a typical vehicle response. We also get nice summaries of the runs and the plots showing the various responses. The agent even updates the model with the calibrated parameter value. That's a huge amount of work that has been completely automated by the agent. Now that we have developed the individual components of our system model, we assembled the entire model that would be used to conduct virtual experiments for the brake system. We used the auto layout capability to generate the graphics for the model. Here we see the icons that we added to the individual component models. But this auto layout is not just a static layout. It represents the starting point for the engineer to continue working with the model graphically. Here you can see that this diagram is live. The components can be moved around the modeling canvas and the connections can be deleted, created, and modified. The system model, which was created entirely by the agent based on high-level queries from the engineer, is now fully implemented from reusable parameterized components and is fully graphical and ready to use in Dyad for ongoing development and experimentation. Depending on the experience level of the engineer and also their familiarity with the modeling tools, this entire modeling process could easily take a day or even more to accomplish, but here we have our answer in a matter of minutes. The future of engineering tools is here, and it leverages AI as an integral part of the engineering workflow. Contact us at sales@juliahub.com if you have any questions or would like to try these tools.
So yeah, if you've been writing all your ODEs yourself still, that should probably excite you, but also scare you. But yeah, I mean, I'll take a bunch of questions, and again, I think that I kind of went over in the first part, so I didn't have enough time to kind of show you how running Dyad myself here to be able to show you that these are not pre-canned videos. Again, we do this as a live stream now, so I'd love to just take a question from the audience here and just have it generate the code and everything. We'd be pretty surprised at what kind of models it comes up with. But so does anyone have well, I guess let's just do something like create a basic energy balance model, EBM, of the Earth. All right. Yeah, because if people want to start playing with this and everything, we can start to see if we create a basic energy balance model, it's going to have to do a bunch of iterations to make sure it gets the right equations and everything. And you guys, we can get some feedback from the audience who will say, add this to the model, add this to the model, and you'll see within 2 hours how much of a climate model we can end up with. And it's kind of a fun exercise. So again, if you haven't been using these kind of agentic tools for coding yet, you should be, again, both scared and excited, right? This is a very different way to be doing coding. If you haven't been using AI machine learning in your coding yet, hopefully you start to use something like Claude Code, or if you do a lot of things where you're doing a lot of modeling and simulation, you can check out Dyad. We can help you get it up and installed and running. Again, because it has all this special static analysis and everything in the context of creating differential equations, it ends up being a lot more accurate than Claude Code. We have a paper coming out next week that quantifies this. But we'll be happy to get you up and running with any of these tools because we think that the whole Julia community should at least adopt them to some extent. So thank you.
Do we have to have questions at all? Or? Yeah. Okay. I kind of just wanted to get back to this denial question I asked before and maybe add a layer to it, which is essentially what you demonstrated, right? I could imagine somebody having the same presentation, but towards writing papers and reviewing them, or writing, say, NSF proposals and reviewing them. Do you want to discuss this a bit? Or give
Yeah, I
your
mean, you know, I'll tell you right now that I have the agents set up on my Overleaf and a bunch of GitHub accounts, and I would give them prompts like, so for example, one of the really nice things to use them for is if you have a database of a lot of grant proposals that were not accepted, right? Again, you know, 15% of grant proposals are accepted or whatnot. If you have this whole backlog of different things, I had Alan send me an email that said, oh, hey, look, you know, MIT needs an internal, you know, they sent around some internal thing, I forget exactly what it was like, you know, forward or something. It's only like $300,000, so like, you know, like let's put together a grant request for this by the end of the week, right? I didn't want to spend time on it, so I just sent a prompt to it that just say, take a look at one of the grants that were not accepted before, make a 3-page version of one of the NSF ones and send it off, right? And it wrote it, and I didn't spend more than 2 minutes, sent it over to Alan. Alan was like, oh, that looks good. You know, so it got an independent check. I didn't tell him afterwards that it was completely prompted, but you know, and yeah, so we put out the grant. So, you know, again, grants that we wouldn't have applied to before because it would have been too much work. If it's only 2 minutes to regenerate it from a different grant we already had, just do it. Just, you know, so we're using this to slam out a lot more grant applications, and I assume that everyone else is doing this too. You might as well just, you know, if it's that much work, you might as well just apply to 10 times as many grants. And so yeah, if you're not using this, if you're still writing it by hand, then we're going to be flooding. That's part of the plan, and I assume that everyone else is going to be doing this too. For papers, I think it's a bit more difficult with papers because it's very difficult for them to write things that have any sense of novelty to them. And so it's very good for them. I mean, I think like, okay, take a 20, 30 page NSF grant and turn it into a 3-page internal grant for like a lot less money, right? I think that's exactly the place where they work out really well. If you try to ask it, you know, write a new novel grant, you know, for that's 20, it's just going to basically spit out things that's, you know, people have already done. So it really kind of requires that you create a lot of source material for it. I mean, and you can see that with DIAD as well, right? You know, we create a lot of source material. If we create, you know, vehicle models, we create multi-body models and all these things, and it's able to compose it, you know, it's able to say, okay, I can take a friction brake and I can take this, I can take this, I can stick them together, right? It could summarize and it could stick things together, but it's not really good at creating new things. And if you kind of keep it within that mindset, then you go, okay, what I'm going to use it for when generating code is I'm going to use it to tell it to create new tests for me. I'm going to use it to you know, improve the performance of my code, but I'm not going to have it try to create a new ODE solver. It'll fail every single time. For my grants, I'm going to have it, you know, like if I have something in NSF form and I need that grant in NIH form, oh, converting it, perfectly fine. Converting it and, you know, turning in for a Simon's grant, perfectly fine. Writing a new grant based off of something, terrible. And so it tends to see that it doesn't do so well with writing papers because by definition, those should be new. But taking that paper and then, you know, making it, summarizing that as one paragraph as part of a grant, and then like saying, and then writing the next paragraph for how, you know, what your grant aim is for your next part of this will be, that's perfectly a good use case for it, right? So I think the key to all this, I think, is they are not good for everything. They're good for some things, and using them effectively is the way to make them productive.
To the extent that it's not like a trade secret, can you talk a little bit about what level of work needs to go into making something like DIAD? Like, is it just kind of open source tools with the first kind of thing that you would think with, like Reg or something like that, or do you need to put a lot more work in to make it actually?
There's a lot more to it, and if Vinas didn't get sick, he would have been here at this to be able to talk a lot more detail into the agent orchestration that he's been building here. I think that there's a lot of what goes on here is this making it so that way it knows what to read, and a lot of prompts around, okay, if you see these kinds of error messages, and then start to look into this, and so it has this like entire workflow of tools where it starts to say like, oh, I could diagnose that this is a numerical stability issue. Okay, if it's a numerical stability issue, what should I start looking at? Okay, I should take the solver, I should put it into this different mode. And basically what we've done is we've encoded the way that, you know, a lot of our expert modelers actually looks at how do they fix their equations, and we've turned that into this is how people do it, so do all these steps. And so we basically, every single time we have new, you know, models that people are debugging, we're just capturing that as new prompts and new setups, and then we have our own agent orchestration for this. So this actually, what we're doing with DIAD still uses the Anthropic models, but it has a very different system for how it's using this information. You can actually see a little bit about this as well. I mean, so for example, in ordinary DiffyQ, we have we have a pull request that hasn't merged yet, which is on the if you can kind of see the kind of stuff that's going on that's like helpful towards DIAD. We have a new logging system that's coming out. Again, there's some things going on with the pull request, et cetera, et cetera. But so, for example, one of the things that we did is we said, okay, the agent needs to have a lot more information about how the ODE, why an ODE is failing. So we end up creating this new verbosity system where, let me see if there's a good page for, inside of core here, verbosity, right? So I'm creating this new verbosity system where it has all these different modes. So in the standard mode, what it does is it doesn't tell you about what happens with the linear system. It doesn't tell you about the nonlinear system, all these like extra little details. But there's all these new switches inside of there for it to be able to say, okay, for every single step, tell me what the error estimator of the step predictor was saying. Tell me what the condition number of the Jacobian is. And so you can make it so that way it prints basically like an entire gigabyte of information for every single ODE solve. And then we're basically teaching it how to read all this information to learn, okay, if you see this kind of information, this means you have a singular Jacobian. This means you have, the type of behavior that would come from a DAE that's changing index. The way that you would fix this is this. And if you see this kind of behavior, so if you see steps failing, but you have high EST, then what you have is you have a numerical instability inside of the linear solver. So change the linear solver from an LU factorization to an SVD factorization. And so we're just building up this bit of knowledge that's just every single thing that we know about numerical analysis with how do you query the ODE solver for more information for how to be able to capture this. And, with a team working on this, for the last, few years and whatnot, we're able to build quite a bit of information in there. In fact, at this point, I don't even like to debug ODEs myself. If you give me ODEs, I like to use the DIAD engine. And when the DIAD engine goes wrong, I like to improve the DIAD. I tell it more things to look for and then, basically just kind of do that instead. So we're basically just trying to say, instead of trying to solve anything ourselves, let's just keep on improving the agent's ability to debug. And if you do that with a big enough crew, it starts to outperform what most people are able to do. And so there's that aspect of it, plus the language aspect of it is a huge thing, right? It's a language-built like modeling toolkit, but it has more static analysis capabilities. And having the static analysis capabilities makes it so that way it's much better at being able to catch errors early and often, and that makes the iteration process much smoother. So I think, it kind of is like these two things together of it knowing a lot about numerical analysis, plus it having a lot of constraints on what is an acceptable model, right? Models have to have the right units, everything has to be connected together, et cetera, et cetera. Those constraints in what you're allowed to write really improves the agent accuracy a ton. And so we're just kind of, again, it's still kind of early in this process, but we're really kind of spinning up more and more people in that team. We're getting, a lot more of this information from a lot of, how a lot of, industrial users and, building airplanes and everything, how they're using this, iterating on the tools around that. And it's at a certain point, I think that it's less about what is like the proprietary, like what is the agentic system looking like. I showed you a lot of my open source one that I use in SciML, right? But it's more about what is the information that's baked into there, about what it knows about debugging ODEs, what it knows about the physics of equations, what it knows about HVAC systems and vehicle models and all that. That can be that is the proprietary information that I think is much more difficult to kind of put back together. So yeah, very good question. And yeah, while this is running, right, so while we were talking, it created an energy balance model, but then it realized that it didn't get to something that was a realistic model, so it actually asked if it wanted me to add something to it, and so it added the greenhouse effect. So let me actually take a look here where we are with our energy balance model. So our energy balance model here, so we have a temperature, we have incoming thermal power, we have outgoing thermal power, we have the solar constant, we have Stefan-Boltzmann constant, we have the Earth's albedo, which is just one piece here. So as someone who's done things like these kinds of albedo models before, I'm thinking, we could probably do this with different latitudes or whatnot. But okay, but then it was able to come up with, we use Stefan-Boltzmann law plus incoming solar radiation. That's a very basic energy balance model, and we can continue to prompt the agent to improve this as well, right? So you can see that it's already starting to get on its way to an EBM, but there's still a lot more to do. So I'd say let's make it a paleo climate model, include some of the corrections from the Boudico model, Boudico sellers model. Right, and we'll see if it can figure this out. So, actually, the first research project I ever did was in paleoclimatology. So that's why I know about EBMs. But yeah, let's take the next question.
Yeah. So I'm definitely not an expert on this field of modeling and all of these equations and all of these systems. I'm out of my comfort zone here, way out of my comfort zone. But I do have to deal with the applications of these models sometimes, and I tend to notice that a lot of these applications that are used to provide as tools for modeling. They are built with really old languages, such as Fortran or close to that. And a lot of the dependencies of those libraries are also archaic, and it's difficult to sometimes even install some of these old dependencies. And you end up having to have, a separate runtime environment on a container or something just to make the thing work. I was wondering, could this be used to you were generating tests with the variables as constants. The question is, could all of these dependencies of these modeling tools and the tools themselves be ported to Julia, for example, with the help of Dyad?
Yes, yeah. So I think that's a great question. So I think the first thing to ask is, okay, why should we just be using some of these tools on the Fortran directly? Because it's if I no longer have to learn how to build these runner scripts, right? Because I could just have the AI write the runner script for me. So why change to simpler languages at all? Why not just keep to Fortran, right? I think that I would start with that question, and I think that what we really see from the Dyad project, again, the paper that I'm referencing here has not quite come out yet. So we're gonna have to wait another week before all the details about what I'm saying here about how Dyad is much more accurate than Gemini and Claude and these things. Right? That paper is I know the results, but they're not out yet. But the reasoning behind a lot of the results that we get, though, I think it really stems from the separation of concerns. Right. So when you end up writing a lot of this kind of Fortran code, right, you're writing both the model and its implementation together, right? You're not writing a code that says, okay, here are the equations, and then a different code that says, oh, here's how I compile these equations to work with a GPU, right? The code has, here is how I do the SIMD, here's how the right way I'm going to do the loops, here's how, everything about the implementation is mixed with what is the actual equations of the model, right? This is something that many other people in this room have talked about, right? This separation of concerns aspect. I think one of the things that we're really seeing is that if you do not have separation of concerns, these AI agents get really, really messed up because they start wanting to do things like, oh, I want to change this equation. But if you want to change this equation, suddenly it's like, oh, I need to change the way that I'm putting things on GPUs. I need to change the way that I'm, MPI distributing everything, right? And so if you have, it starts to mix it up because you can no longer make small changes at a time. You have to make very global changes in order to do anything, right? And so what we're seeing is what we're seeing then is you could maybe start to use these tools on these kind of Fortran models, but the lack of separation of concerns, that mixture of implementation with the model itself, really ruins the accuracy and the ability for these tools to work. So this then gives us the reason to be moving a lot of things to Julia and Dyad, which is that if we can construct programming languages for which the implementation is so whether you run it on GPU or CPU is separated from how the model is actually written, right? So you say, oh, I have a vectorized piece of code, and if I give it a CPU array, it runs on CPU. If I give it a GPU array, it runs on GPU, right? That separation of concerns makes it much more easy for the agent to be accurate. And so then because of that property, then trying to take code and using these tools to do the translation ends up helping, right? Now, using these tools actually came first, the first places where large language models were used was actually for language translation, right? I mean, it was used for Google Translate, which is, English to French and English to, to Portuguese and all this, right? So it's kind of a different problem, but it does mean that these tools do end up doing quite well at language translation. But what you normally want to do is, again, they only work doing small things at a time. So doing something where you say, okay, translate this file to do the direct translation of it from Fortran to Julia, and then you say, okay, now test this. Now after I get this, well, I probably don't want to use for loops. Change the for loops into broadcast, and slowly merging it to being something that's more general. That is an approach that seems to do fairly well. In fact, the thing that I'm skipping over here because of time is we actually have that the other thing is translation between different modeling languages as a part of the dyad system that's actually been able to do so. It has a whole corpus of different models and how to do the translations, some manual steps in there, et cetera, et cetera. And so we actually using this for doing translation to simpler languages to then allow the agent to run on it on the simpler language is one of the main use cases that we are seeing for this in the future. If I had more time, I would go into that bit as well. I'm talking about this from Modelica to Dia, but it's also the same thing of changing from Fortran to Julia. I mean, you can use the purely open source or the purely Claude, Gemini to be able to do this. If you use the pure ones like that, I would say you probably want to create your own pipeline, which tells it to do it step by step and breaks it down into just do a direct translation, now change the loops, now change this, now change this. It'll be a lot more effective than to say, oh, translate it and turn it into nice Julia code, right? If it doesn't do it step by step, it will fail. But they do well if you do break it apart.
I would say test by test, right?
Yeah.
If you want to translate effectively, you will get the old system. You will get a huge battery of tests to characterize the old system, and just make sure the new one is in accord.
Yeah, and in fact, what we do with the Modelica to Dyad kind of engine, and you can kind of build this on your own for very specific kinds of things, right? Is we say, okay, take the original code that you have, now build a binary of the original code. You can use that binary as a source of truth, and then build a bunch of unit tests, just putting in random values into here, and so that way we can know how close it is to this source of truth over a wide space of parameters. And now, as we do the translation, translate one piece of the code at a time, and be inputting C calls and things, so that way you're still using a lot of the original code, and one piece at a time, get one script correct, and now it's matching all the values, get one script correct, one matching all the values, and if you slowly make it so that way it's pipelined that, then it's able to be fully automated. If you try to tell it one shot, do the whole translation, it's going to fail every time. So, I mean, especially with Fortran, right, you can do this nicely with Julia because, you can C call into Fortran, so you can say, hey, here's all my, now expose all of these functions, create a binary that exposes all these functions, now translate this function in Julia, but then replace this function right here with a C call to the original Fortran code, write unit tests here. Okay, I got this function correct, do the next function, do the next function, do the next function until it's all correct. That ends up working quite well, yeah.
Yeah, so it's sort of a related question, but essentially it is, what do we call the Julia language? Because in your presentations, you've emphasized the need to put constraints around things. Julia has this great power that it allows us to abstract things in many different ways. That becomes a potential source of difficulty because the language itself, if you include especially the effervescent development that happens outside of the Julia world, is never defined what it is. Right? It can be any kind of thing ultimately. So what's your sort of sense of that? What is the Julia language?
Fantastic question, right? And I think it's evolving. I think because of the way that these LLM tools are changing how we do programming, I think it's actually changing what we're thinking the right language has to be, right? I think that Julia has the right baseline for this, right? And the reason for this is that you can think about Julia as a gradually typed language, right? Where it's a language where you say types are not required, but you can start to put types in there and have type information, right? And I think that's exactly what you kind of need for these agents to start to work, right? Because if you take it and put it on a system kind of like Rust sometimes, right? It will be very difficult for it to figure out how to get the first thing to run and compile, and it might give up halfway. That's kind of difficult for it, right? Now, if it tries to start writing something like Julia code, sometimes it will just, it'll create bad Julia code to start. It might allocate a lot or something, but it'll get the right answer, right? And this kind of property helps the agentic system work a lot, right? Because what it needs to do in order to do this iteration process is it needs to be able to write a bad code that gets the right answer, and then make it more performant, and then make it so that way it's type stable, and then add allocation testing, add jet testing, et cetera, and slowly turn into something that's more static, right? And so you can actually see this live happening. I mean, it's probably happening as I speak inside of the ordinary DiffyQ repo, right? I mean, some of the things that it just came up with is just saying like, oh, there's some jet tests. It needs to add jet tests to be able to make things more static, right? And so it's live trying to just figure out how do I make things more static, and turn this into something that's more like Rust code, but step by step by step on different pieces, right? I do think that this is going to change the structure of the Julia language down the line, and the way that I think this is going to look is that I think that there's going to be a subset of the language that'll be like a strict subset that will act more like Rust. And so what you'll be able to do is you'll be able to say, hey, look, the starting point of our language is it feels like Python. And the reason is because it's very easy for the agents to be able to guess what code is like and run like this. But I can merge my code to be something that's now compatible with like trim, making small binaries and things that we heard about with JuliaC. That actually has a lot more constraints to it, right? And so what we're doing right now is you can add tests to be able to say, okay, I want my code to be able to still satisfy all this. But I think the last little bit to this is actually just have that be a well-defined subset of language, call it strict Julia, that then you can say, okay, now I want my code to be able to run in strict Julia by the end, right? And so then you can have this process where you gradually go from a code, again, it's all in one language, it goes gradually from a code that's very dynamic to a strict version that then requires static behavior, and in that version it can have more static analysis. There's actually open pull requests and discussions going on in the Julia repo for what the definition of the strict mode would be. And within Julia Hub, we're already starting to try to build out that strict mode because we need it for some of the things that we're doing in the dyad space. So I believe, so again, there's many ways that the language can evolve or whatnot, but from working with the compiler folks and everyone directly, seeing how we're working with it with the agents and everything, I believe that this is the language of how it's evolving, and I think that this is the language that needs to exist for agentic systems. Because it's very difficult for them to get the strict mode perfectly correct the first time, and if they don't have anything, if they don't have anything to start on, they can't start this loop to improve themselves. So I think that is kind of the optimal space there of making something that's easy to hit to get that first version, but also gradually able to get more and more type information, and then lock down and say, okay, now do not accept any code that does not meet these stricter constraints. And I think that Julia will become the language to do that. There's a lot of work that's going to have to come towards that, but I think you can start to see that in things like the JuliaC and the trim compatibility, all the jet testing and everything. You can start to see the foundation of this being laid out. Oh, thank you. Thank you, everyone.
Thank you very much, Chris, for the wonderful sessions this morning on a hands-on introduction to applied scientific machine learning and accelerating modeling and simulation with specialized code agents. Your insights and examples were truly inspiring. We will now take a lunch break. Lunch will be served from 12 to 1. Please enjoy your meal, and we will reconvene here at 1 for the afternoon session.
So if you are online, this is the end of the day for today. We'll see you tomorrow at 9 a.m.